Okay. We can start, I think. Thank you for coming back after lunch to this session. The previous chair wanted to take a nap after lunch, and so he asked me to be here in front. It's my pleasure to present you Dimitri Bizicalo. So there was a change in the program, as you can see. And Dimitri is going to speak in the place of Alexei Pozhanenko. He's going to talk about possible electromagnetic manifestations of merging black holes. Thank you, Dimitri.
Okay. Okay, dear colleagues, the official title of our meeting today is multi-messenger and multi-wavelength astronomy. And you know that recently LIGO and Virgo found actually opened a new window. It's a gravitational wave that gives us some new information, and it's a real messenger. At the same time, we know that the majority of all measuring cores found it's measuring of black holes. By definition, measuring of black holes does not provide any electromagnetic observations, manifestations. It means that for most popular and most frequent events like measuring of black holes, we cannot speak about multi-messenger astronomy. And therefore, I'm trying to show you some results of theoretical studies where we will show that in some cases, the electromagnetic radiation is possible, and we can speak something about multi-messenger astronomy for measuring black holes. This work was done in my home institute, Institute of Astronomy of the Russian Academy of Sciences, in collaboration with Andrei Zhilkin and Evgeny Kurbatov. This list of okay, it's too complicated. This list of first published gravitational events that were obtained during 2015-2017, and these 5, all of them are measuring of black holes. Here you can see masses of the components, both components, the relative change in mass in percent, I guess, and the distance to the object. After reprocessing of this data, colleagues from LIGO published actually a catalog containing 11 events. And one of them, it's a neutron-star merging, but the rest 10, it's a merging of black holes. We are quite conservative, so we prefer to use the first published data and actually to use the latest event observed with LIGO. It was done in August 14 of 2017. It's the time when all instruments were in a good order, so we hope that these data are quite reliable. And you can see that the masses of the components is it's a solar in solar mass. It's 30 and 25, and the total mass loss is on the level of 5%. This event was quite far from us. It's 540 megaparsecs, but still it's a quite reasonable value. Here you can see a standard set of gravitational signal, and I'll skip this slide because all of you know well this problem. And using the big data, because we computed a lot of models. People from LIGO define the masses and other parameters of this event. Okay, so it's a new window, and the question arises how to get electromagnetic response during merging of the black holes. One of the clear possibility, if you have some material surrounding the black holes, it should be some response, and you can see something, I mean baryonic material. You can see some signal from this event. You know that in studies of black holes, it is quite usual to assume that there is some accretion disk around black holes and to observe them in AGN and our bright things. And it is quite possible that around binary black holes we also have a circumbinary disk, because here you can see the time between before coalescence, and it's quite long, so there is a possibility that we'll get enough material to form the accretion disk. This problem studied quite well in supermassive black holes, and people consider a lot of different scenarios, like collision of galaxies, different kind of galaxies, and all times we have some rest accretion disk. In stellar mass binary black holes, the situation is a bit more complicated. While we have a few already classical papers where indicate that accretion from the third component or tidal disruption of the third component can produce the accretion disk. At the current days, we have a few more bright ideas, like fast rotating star that can produce the material around binary black holes. But it doesn't matter. We just assume that we have some material around the binary. Here you can see some simulation of the binary stars surrounded by circumbinary disk. And if we can see the merging of binary stars, we can easily estimate the influence of this effect on the system itself, because we should see the decrease of the rest of the mass. It was published first many years ago, and emission of linear momentum can produce a kick. It's also not a new idea. It was published first in 1962. And depending on the Wimber's ratio and our parameters, we can say that the delta M to M is less than 10%. So we should wait that the mass loss change should be on the order of 5 to 10%, and the kick velocity is less than 1,000 kilometers per second. If you have a disk, the emergent black holes will also influence of the disk itself. And the first effect is quite clear. But if you suddenly remove some mass from the center object, the quasi-Keplerian disk around this object will be not in the balance will not in the balance anymore, and you should get some waves and other stuff. Gravitational wave radiation may be asymmetric, and as a result, the disk will experience a kick, which can lead to the emergence of supersonic perturbations. And third important thing that changes in the space-time metric in the gravitational waves can directly lead to mechanical stresses in the disk. This idea was proposed in 2008, and in 2016, Anatoly Cherepashuk predicts that it could be a shock wave in this case. You know that a lot of studies were made for supermassive black holes because people assumed that it's most powerful events in our in the observations. And I just briefly summarize when all of them, but if binary black holes losses on the level of 5%, the total energy output will be on the level of 10 to the 43 erg per second. For stellar mass binary black holes, it was a few papers, and probably first one was published. Actually, it's not a paper; it's just an abstract. Was published in 2007, and Selma Deming and Andrew King summarize all these possibilities and estimate the energy of the electromagnetic output on the level of 10 to 43 erg per second. And all this were made assuming that all these waves that can be produced in the accretion disk is a density wave, but on the other hand, there is a possibility that it's a shock wave, and in this case, the situation will be a little bit different. Here you can see just a few explanations. That you have old orbit, it's shown by red circle, and if you assume that the mass loss on the level of few percent, we should get a new eclipse. It's shown by blue, and actually it means that any circle in the center of the accretion disk will expand and will form somehow the density bump at the inner edge of the disk. And if this bump will expand to outer part of the disk, and if the velocity is high enough, it can produce the shock wave. It's clear that this mechanism should work everywhere in all circumbinary accretion disk, but it's practically impossible to say analytically how much energy will be emitted in the electromagnetic part of the spectrum. So to study this, we made quite sophisticated simulations, and I will show you some results of these simulations. Few words about problem setup. Again, we have a crater. It's already total mass. It's at the beginning it was 30 and 25 masses black holes. The total mass is 55 solar masses. There is some difference between accretion disk of the binary and single star, and the difference mainly compressed in the inner part of the accretion disk, because for this part of the disk we should have the gap, so-called gap. It's produced due to tidal distribution, tidal distortion, and also due to gas dynamic evolution of the disk. And this gap has a typical radius on the level of a couple of separation. The fast merging started at the level of 6 Rg, so we can assume that the typical size of this gap is on the level of 10 Rg. And for us it's very good, because in this case you can assume that disk is close to Keplerian one and can be described by Shakura-Syunaev theory. It's not a relativistic disk. Okay, in the radius of the disk, as I already told, it's 10 to the 8 centimeters. We assume the thermal structure of the disk, that thermal structure of the disk corresponds to so-called zone B. Accretion rate is 0.5% of the initial mass. And we also, I show you a few different runs, but we started from gas pressure dominated disk, which is quite reasonable for this disk. And here you can see the results of analytical work made by Shakur and Sunyaev already practically 50 years ago. And with the temperature distribution and density distribution of this disk. And at the initial time, the mass of the crater is reduced by 5%. Here you can see the set of gas dynamic equation. It's more or less typical. The disk was assumed to be equilibrium, and you can see the different solutions. Actually, it was different temperature of the disk, that corresponds to Mach number 100, 150, and 200. And yes, it's very important. First, we tried to solve this problem analytically, and we used practically the same distribution as it was in the Shakura-Sunyaev solution. And we found a self-similar solution on this disk. It's a great job, but unfortunately we cannot finish it because we cannot realize where the shock wave should be located in the disk. Here you can see some caustics that exist in the accretion disk, and the presence of caustics clearly indicate that we have a shock wave in the disk, but we cannot realize where it should be located. So we change our mind as usual and start simulate the same problem. As I already say, we run 3 cases for different Mach number, and here you can see the with the radius and with the density profile, and with the same profiles for what corresponds to this part of the curve. And it's clearly seen that we have a shock wave in the solution, and for a small Mach number, we have even a couple of shock waves in this. What does it mean? That means that we have some additional heating of the gas, and because temperature increases, it means that the luminosity of this shock wave will be significant. And here you can see temperature as a function of radius. Again, the same temperature dependencies for different Mach number. And this table shows how much temperature changes in the solutions. And you can see that for Mach number 200, it's on the level of 30. It means, and you should remember that temperature is the 4th order in all equations, so it's a huge difference in comparison with density wave. A few words about, okay, all these runs were made for mid-plane of the equatorial, for the accretion disk, so, but we need the temperature at the outer edge of the disk on the Z direction. And we tried to estimate different, how the temperature at the boundary depends on the temperature in the inner part of the disk. In our case, we have a quite large optical depth, and actually, if we assume that the thermal energy is carried out by radiative heat conduction, the difference between this temperature should be on the level of 10. On the other hand, these disks are close to stability for convection, and it's quite possible that this disk is convectively unstable. And in this case, the difference between surface temperature and temperature in the mid-plane will be on the order of 0.6. It's well-known results. We assume in our paper that the temperature, surface temperature is 2 times less than the temperature in the mid-plane, assuming that it's a convective disk, more or less convective disk. Okay. shock arising in the disk leads to temperature increase, and as a result, the gas in the inner part of the disk is heated to a temperature 10 to the 8 Kelvin, and under this, generally under these conditions, because we should consider just electron Bremsstrahlung and Compton scattering, we can assume that the radiation from the disk surface has a Planck spectrum everywhere, and this is corresponds to these equations. And here you can see changes of the bolometric luminosity of the disk with the time in seconds from the beginning of the process and with the luminosity. And you can see that the upper level of this luminosity is quite high. It corresponds to few 10 to the 45, and it's quite large number. And the spectral flux density of the radiation from one side of the disk can be described by this simple equation. Concluding this part, I would like to say that formation of the shock leads to increase of the luminosity in the disk up to 10 to the 45 erg per second. At a distance to the source of 540 megaparsec, the flash will be as large as minus 13 magnitude, and the maximum radiation flux lies in the hot X-ray range. Okay, but as I already told, we consider a different model, and second model take into account the radiation pressure, because it's a quite high temperature, 10 to the 8 Kelvin, so it could be that this radiation pressure decrease the temperature behind the shock wave. And the second important effect is gas expansion in the vertical direction. 2 minutes, 5 minutes. Okay. Okay, this is a solution with the radiation pressure, which is important with this value beta. It's gas. It's a thermal pressure to the total one. And again, we consider two type of disk. It's a convective disk with difference of the thermal, with the surface temperature to the mid-plane temperature equal to 2, and radiative disk with equal to 10. And here you can see results for convective disks, and this is results for radiative disk. And this total the sum of these results for shown by red for radiative disk and blue by convective disk. And you can see that the total energy flux in this case corresponds to 10 to the 43 erg per second. Actually, it is quite important, because here you can see the luminosity of this event. And this it's a spectrum in different definition, and this green line corresponds to a peak at XMM Newton, and you can see that it was quite possible that this event can be observed with a peak. So it is clear indication that we can get some electromagnetic signal from merging black holes, and it's in this case, it will be really multi-messenger astronomy. Okay, and the last part is the model. It's a more complete model. We model with radiation and vertical expansion. I'll skip all these equations, and the result is on the level of 10 to the 40, few times 10 to the 42, and this is the summary results that indicates that with some probability, with high probability, we can observe this with XMM Newton. There are a few additional physical effects one can change this solution. I mean, magnetic fields, but I'm not sure in which direction it will work. But generally, all efficient mechanisms are already in the model, so we can more or less trust to this data. Okay, and with my summary, with in convective, okay, this is actually, this is my summary. The loss of 5% of the mass lead to the formation of the shock wave, and it's clearly seen both in analytical and numerical results. And presence of shock wave increase the electromagnetic luminosity of this event. Maximum radiation flux lies in the soft or hard X-ray range. Flash duration is a tenth of seconds. It's unfortunately it's very short event. And the flash is available for observation XMM Newton and spectrum RG. Especially if we, okay, it's just a few more words because it was calculated for very far event at 540 megaparsecs. So if this event will be closer to observer, we'll get a more strong signal. Okay, so we can be quiet because the multi-messenger astronomy exists even for black holes. Okay, thank you very much.
Okay, so Alexei?
Thank you. Thank you for interesting talk. Can you hear me? Okay. So my question about a few questions, but last one: how can be your flash can be detected by Rosetta or observations? Because it is in scanning mode, and the flash, the probability is equal to 0.
No.
Why? It's a duration
Okay,
of 10
it's not
seconds.
a 0. It's close to 0, but it's not 0.
Okay. But we are.
You should be, okay, the answer is very simple. You should be lucky.
You should be lucky.
Observers should be lucky.
Okay.
If you have the telescope oriented on the event or close to this 10-second event, you can observe. And unfortunately, there is just one probability to have some electromagnetic signal from emerging black holes, because no other ideas, all of them give a much less electromagnetic signal on this.
So the second question. So you said about non-uniform emission of gravitational wave.
Non-uniform.
Non. Oops. It was. Could you speak? Could you go to the some second or third slides? So
Okay.
anyway, so the question. My question is related. Is it not that exact? Is it could be a recoil from merging of black holes? If yes, but I believe that it could
Yes,
be. It could be. What's the impact on your result? Recoil, or if it is
Yes,
stronger in the tropic?
Yes. Okay. The problem that if you have a recoil, you can produce some electromagnetic luminosity. And Andrew King and Selma Deming, they estimated this value. It's 2 orders of magnitude less. But even if you have non-symmetric and shock wave, it will be at different times. So you can see first the shock wave, and then sometimes you can see the radiation from the kick. So
it will be 2 different episodes
Yes.
of emission. Okay, thanks.
Yeah.
Sure.
I hear you. You can.
Just speak louder. Just speak louder.
See, now it is switched on. So I did hear your question, just a very faint. So, one question, one comment. Question is, I don't understand why you took temperature going as radius to the power of minus 0.9 instead of the standard Shakura-Sunyaev 0.75.
No. In Shakura-Sunyaev solution, we have three different zones. It's zone A, zone B, and zone C. Zone B and zone C, it's more or less, and this is exactly from the solution. I reported these results to Shakura, and no objection from his side.
No. I'm just saying that observationally, X-ray astronomers usually always fit disk spectra, and they fit very well with a slope of 0.75. So it's interesting to see what the difference is.
It's for radiative dominating disk.
Sure. Okay. So and the comment was that maybe a better instrument to detect these kind of things would be Einstein probe. The Chinese satellite is doing the monitoring of a large 3,600 square degrees for each image. Maybe that will have a better chance to...
You're quite right. I am not an observer, so you should realize. And my idea was to show you that there is a possibility to observe electromagnetic. And if you have any idea how to do this, because initially we plan to estimate the response in ultraviolet, because we have ultraviolet project. But in ultraviolet, it's impossible to see anything, except it will be very close to the Earth.
Yes, and thanks for your talk. Could you say something about for instance, the mass which is lost that you mentioned? 5%, a few percent. Can you say something about how is this mass loss distributed, spatially?
Lost mass distributed.
Can you say, yeah, right.
Yes, it's it's just after Einstein. It's a gravitational waves. It could be symmetric, it could be asymmetric. If it's asymmetric, you will get some kick. So it's absolutely standard theory. So I can say anything new. Yes, of course, sure, yeah.
Okay. I think that's everybody.
Okay, thank you.
Let's thank Dimitri again. And now we go for our first attempt of a remote talk. Let's see how it works. So the talk is going to be by Kanak Saha, and let's see. Okay. Bear with me. Hello?
Hello? Can you hear me?
Hi, we can see you. Can you see us?
Yes, I can see you. Hello, everyone.
We are very well, thank you. What time is there? What time is it there? Hi.
It's 11 in the night.
Okay. So let's start so that you can have some sleep. Maybe are you going to share your screen?
Yes.
Okay, you can go ahead. We can listen you perfectly.
Sure, I'm just trying to see the share the talk. So the can you see the screen?
No, not yet. We still see your video.
I think I would disconnect myself and share the screen. Sorry. Okay. Can you now?
Yes, now we can see ourselves. Yes, okay, good. Perfect.
Okay.
So I will ask you, Saha, to speak slowly because it's more difficult to understand from the remote connection. But otherwise, we can hear you well, and you can start. You have 25 minutes, then we have some questions, okay?
Sure. Thank you.
Okay, thank you.
Yes. So first of all, I'd like to thank the organizers for giving me this opportunity to present this talk. This is about AstroSat and its UV ability. In that, I would just give first a bit of an overview of the AstroSat and the UV telescope, and then I go to some nearby galaxies and clusters being observed by AstroSat. So this is the AstroSat, the orbit. This is an equatorial orbit. It was launched October 2015, exactly almost 4 years ago. AstroSat orbital time scale is about 97 minutes, and it has primarily X-ray instruments. It has a large X-ray proportional counter, the LAX-PC, which works from 3 to 100 kilo-electron volt, and a large field of view. And it has a stopped X-ray telescope, SXT, which works from 0.3 to 8 keV. And then it has also an imaging cadmium zinc telluride, which works from 10 to 150 keV. Apart from that, we have the UV telescope, which works from 1300 angstrom to 3200 angstrom in 2 filters, and is a large field of view, which is about 28 arc minutes. The UVIT telescope, which is on the right side, is the picture of Professor Tandon, who actually the PI of this telescope. This is 2 co-aligned telescopes with each an aperture of only 37.5 centimeters. So it's a very, very small telescope. It has the 5 filters in FUV, which range from 1480 angstrom mean wavelength and all the way up to, like, there is a narrowband filter at the end. Generally, the calcium fluoride, the filter is affected by the geocoronal light, which adds to the background in FUV. Then you have NUV filters. In NUV filters also there are about 5 filters. So we have one broadband filter, which is NUV silica, N242W. And then you have a few others, narrowband filters. So normally the maximum frame rate is 30 per second, which means about 33 milliseconds per frame. If you take the full field of view, then you have the narrow field of view, which can be as high m per second. This is the observing study. And from the NUV and the FUV, it has also a Reese filter, which is mainly used for tracking. We don't use it for any astronomical purposes other than tracking. So, to summarize, FUV and NUV observations are simultaneous. The time between each frame in a normal setting is about 33 milliseconds. A typical good dump orbit is about 150 seconds. So in a typical good dump orbit, you will have about 45,000 to 50,000 frames. So of these, about 10% to sometimes even 20% are removed due to the cosmic ray showers. And so these are like some of the numbers that we come so far. So I show you an example of a galaxy NGC 4571. What you see in blue is an FUV, NUV from AstroSat and SDSS R-band. This galaxy has a little hydrogen gas, probably lost due to RAM pressure stripping, and it's in the outskirts of the Virgo clusters. The typical, like, the smallest clump that you see in FUV is about 100 mega year old. So basically, and the size is about 40 to 50 parsec. So this the FUV observation can actually lead to allow you to understand the star formation history of these galaxies over a time period of about 100 or at the most about 150 mega year old and at a GMC scale. I'll just show another image of the same with HST 55W, NUV and FUV in blue. And if we see in the center, very nice FUV, the rings of the newly formed stars. So this is a galaxy which is basically a flocculent spiral galaxy, and it has not much of H1, but it's forming a lot of stars, and it's supposed to be one of the in the outskirts of the Virgo cluster. So this was something interesting. Then I show you another example of a galaxy, interacting galaxy, NGC 4016 and NGC 4017, and you see this is a H1 contus, and in the H1 you will see at the bridge there is the tidal dwarf galaxy. So I observed this also with AstroSat. You can see the images at the center. This is in black. This is in NUV. I show the highlight. You can see clearly that in the blue, the circle, which is like the bright blue circle, there is the tidal dwarf galaxy. You can see very clearly, and also at the southwest corner, you can see the FUV emission very prominently, which means one can actually study the star formation with the H1 gas. It's very nicely in this. Just to give you an example of this galaxy, which is on the top, NGC 4016, you see a figure of 8, and also you could see it in FUV, which is in black and the white background. You can see very clearly a nice comparison is possible with FUV and SDSS. Typical, the PSF for this thing is about 1.3 arc second in FUV. In NUV, it goes to almost 1.1 arc second. AstroSat also been used to observe regular clusters, NGC 188, in which we found a hot companion to a blue struggler. So this was published 3 years ago. AstroSat also used to observe the jellyfish galaxy. You can see the images on the left by the AstroSat, and a lot of details are possible to study particularly because of the higher resolution. Interestingly, the astrosat also been used to map the M31 bar, the Andromeda. On the right side, you see at the center of the Andromeda, and you see hot blue stars, which is like star forming. So it's in far ultraviolet. Moving on, so I now wanted to get into the bit more specialized, and then the far side of the what astrosat being used. So we created an astrosat UV deep field. This deep field is none other than our old the Good South field, which basically hosts the Hubble deep field, and I'll go into a bit of a details about what did we actually see in this deep field. So the deep field is basically allows you to look into the past of our universe, and HST has done a fabulous job on that. So in going towards almost like a bit more than less than a billion years old when galaxies were probably just forming. So the idea is to in the deep field observation is to basically see when do the first galaxies form, and can we understand what was the mechanism, how did that happen. So I'll take you to very quickly through this very popular slides in which I say only a single the sentence is that our universe is actually gone through a phase transition from a neutral to completely ionized. And what so that's the era is known as an reionization era. Something like reionization ended around redshift 6 and probably started around redshift 10. And what was the main thing what is the main thing that we want to know is that how did this reionization happen? Okay, or what are the sources that were responsible for the reionization? And that's where we are heading to. So in the early universe, just to give you a very quick summary, that the COBE map CMB is produced the heat map of the universe when it was only 0.38 million years old after the Big Bang, and there were no stars, galaxies. It was the darkest place in the universe. We have about 800 galaxies discovered within the first 1 billion years. And when and how did these galaxies form? Stars, whether there's a POP3 stars formation, these are all the key questions that are interesting. And star formation is of course the key to the galactic formation. So imagine the POP3 stars formed in mini dark matter halos, which is about 10 to the 5 to 10 to the 6 solar mass, as the primordial gas collapsed in these mini halos, and typical mass would have formed, which is previously foreseen, is about few hundred solar mass. But if the primordial gas has non-zero angular momentum, then this collapsed gas would form protostellar disk, as shown by recent simulations, and this protostellar disk would be gravitationally unstable and would form it may fragments. These fragments would form like a POP3 stars, which are less than a few tenths of solar mass. So the first galaxies or the proto-galaxies are composed of these stars of UV radiation. Okay, the UV radiation above 13.6 eV gets absorbed by the surrounding gas in the interstellar medium of the host galaxy, but UV photons, which are less than 13.6 electron volt, have long mean free paths, so they can actually travel long distances. So the question is can we catch these sources? Okay, and this is where we are coming into picture. Okay, I'll just quickly skip through this, and then I show the plan what we were doing here. So we actually made astrosat observe this green and the red two fields, which covers almost the entire Chandra deep field south. of course, like it has the good south and the Hubble alternative field. So our observations at like 50 kiloseconds on the green and the 50 kiloseconds on the red, and the combined area which covers the good south has about 100 kiloseconds. So this is what we expected. But then when we got the data, after we clean and the pipeline had gone for like several stages of like refinement, so we actually end up covering only about 60 to 62 kiloseconds of data. This is about one orbit image. I don't know if you can see anything in far ultraviolet. It's only this green dot. So this is how basically one orbit image looks like. What we do is basically, if we have a good orbit image, so we take as a one as a reference, and then we look at the sources. So the green, for example, let's say at t equals to 0 frame, and the red would be like something at t equals to t1. So we apply shift and rotation, and just to stack them together and make the final image. And the final image looks like something like this, which you can see. So this is where in the white squares are the mu deep field, and the blue and the red are Hubble deep field and Hubble ultra deep field. And we will be looking at an object somewhere in the red circle. Okay, just to give you a comparison, so basically the red squares here is actually the Hubble X in this field, and I show you an object here on top with the astrosat extended field. So Hubble extended field, we have done the astrometry like now, as you can see, like we are able to now actually connect from astrosat images to directly to the images made by the HST. And interestingly now that we saw a very nice extended on the left side corner, you will see an extended 3.2. So I go a little bit detail. So we have observed about the good south. This is, you can see in the blue are the extended UV emission, FUV emission from actually the UVIT astrosat, and the pink and the white are basically the green circle ellipse is basically the HST emission. On the below you see the surface brightness profile, where the far infrared and the optical actually ends at around 2 to 3 arc seconds. The FUV emission goes all the way up to about to 6 arc seconds. So almost like factor is double. Okay. So this is something like they're completely new, and then this work is completed. We'll be submitting soon. And then some limits here. So we basically looked at the sky, and then you can see that the sky in NUV is about 27.7 magnitude per arc second square. In FUV, it's like can go even fainter, which is about 28 magnitude per arc second square. In the red square, which I showed in the previous, we made the magnitude histogram, and you can see that in FUV the 5 sigma detection limit is about 27.3, which is pretty good. We compared this with the HST, the UV filters in the same. They are like around 27.2, 3 or 4, like that. But anyway, this work is in progress, so we'll make refinements soon more. Just to give you a comparison between on the left side you see is the astrosat UV field. On the right side you see the galaxy. You can see the source contribution is like much better in astrosat. You can see the magenta circle on the left. You can see in galaxy almost you wouldn't see any galaxy, but here almost you can count in naked eye here in the images. There are about 5 objects there. Okay, so this is going to like change out the source statistics quite significantly, and we expect to like do much better on the faint end luminosity function, the slope of the faint end luminosity function. Moving on, so I will show you a little bit of like one of the first detection of that what I was talking about, the deionization of the universe. So as you might know that the reionization or the object redshift 6 is very difficult because of the IgM attenuation is very severe. So here so all we could do is basically look at the low redshift galaxies. But then you have limit that you cannot observe from the ground from redshift less than 2.7 because of the atmospheric cutoff. And then you can only look at the like low redshift less than 0.4 is from the HST cos. So you have a big window of the redshift 0.4 to 2.7 where it is not possible, and we show the first time that there is a first detection of a Lyman continuum galaxy at redshift 1.42, and at redshift 1.42 you can see that the FUV is completely within the limit. So the source is here. You can see almost looks like a noise here, and within the red circle. And this is what we do the same red circle. On the left you have NUV near ultraviolet, and an FUV within the far ultraviolet. This is about 3.16. So that's in the FUV. So we do detect a signal here, and this is the galaxy. What it looks like in the same in the HST, which is 275 is the near EV equivalent of astrosat, and optical and the IR. And if you look at carefully here, we do not see like any source of contamination. So this is relatively clean source, which seems to be producing the Lyman continuum radiation, and we are observing it through the astrosat filter. And these 4 clamps, we have gone through a bit of an exercise, try to show that all these 4 clamps are actually at the same redshift using HST prism. And this is where I was telling you that our galaxy in the middle, on the left side plot, you will see that this is from the Steidel et al. 2018, and this is the isotope, the green piece, which is emitting Lyman continuum radiation, galaxy, which is at redshift 1.42, showing the Lyman continuum radiation. So it can bridge a gap basically between two redshift prisms. So you also did a lot of ACD fitting and analysis using various available software, and also the cloudy photoionization model. And we just to give 1 or 2 parameters here. So the stellar mass is pretty low. Which is a 10 to the 9 solar mass galaxy, and the star formation rate is quite high. It is about 50 solar mass per year. And this is the GRISM, and in this GRISM in the near IR, you can see, and we clearly detect H alpha, and with the H alpha is at redshift of 1.42, both O3 and H alpha. And then we did also a little bit of more study in this, like emission line mapping. And here we show that through this emission line mapping, we show that all the clamps are actually at the same redshift. So this would be one of the first clumpy galaxy showing Lyman continuum radiation also. So the astrosat basically gives the unique way of catching up these galaxies from redshift 0.9 to 2.2 within this the far ultraviolet. And as you know that there is no telescope with this sensitivity, and there is no such FUV telescope anymore. Okay, so the astrosat is the only one, and one can actually go from redshift 1 to 2, which is basically peak of the cosmic star formation history, and we can understand those galaxies through astrosat. So this is a unique thing to that. We are constantly improving and this is where we show the RMS background, which is going down as we change the exposure time, almost like a square root of 1 over square root of time. The signal to noise ratio also goes over square root of time. So we have a scope to improve. So we are making a big, a more legacy field, legacy survey with the AstroSat, which is the center field now in the green, and this is also being observed, and we will be making the one of the deepest FEV sky in this part. With this, I should thank you very much, and thank you for your attention.
Okay, thank you very much. So, are there any questions from the audience? Can you say something about the operation of the satellite, if it's still operational, and until when the mission is expected to continue operating? Hi. So apparently we were mute. Can you hear us now?
Yes, I can hear you.
So there was a question regarding the operation of the satellite. So do you know, can you tell us until when the satellite is going to be operational?
Well, the projected time was for 5 years, and we are already in fourth year actually. This is the fourth year.
Okay, so there is at least another year.
There are some issues. Yeah.
Okay. Any other question? Well, I have one question. How can we access data from AstroSat or propose observations? Is this possible?
Yes, very much possible, because AstroSat is open to international community, and there is a call for proposal now, which is called a if you need a detail, I can forward you the email, and which you can forward it to the participants.
Okay. Great, thank you.
And data are available at the ISRO site.
Okay, so I think I thought there was a question, but there is not. Well, thank you very much again, Kanak. I hope you can know that the event is being transmitted via the web. So it's in the YouTube channel of our institute. So if you type CBPF YouTube in Google, you'll find the event being transmitted online. So you can follow us. If you, for some reason, cannot sleep immediately. Okay, thank you very much.
Okay. Meeting.
Bye. Okay. Do you have your presentation? Which one? So, as you can see from the program, the rest of the day we started with AstroSat. It's going to be a series of presentations about instrumentation from the different BRICS. And now we have the pleasure to present a talk by Patrick Wood about Meerkat and Meerlicht. Okay, go. Thank you.
Okay, thanks. Much better. Brilliant. Okay, so these are large teams, as we talked about earlier, and much of the work that I'm going to show you are in fact efforts by team members and students as part of the collaboration. So the talk is largely built around this. I'll give you a brief overview about MeerKAT. And of course, this is a precursor to SKA1 MID, the mid-frequency component of SKA. And then I'll go on to the MeerKAT large surveys. Again, Russ mentioned this briefly in his talk this morning. ThunderCat is one of those large legacy surveys, and we've been in operation on MeerKAT for the last year. So since July last year, since the inauguration of MeerKAT, we've been taking observations of a range of transient objects. So I'll give you the objective of the survey, what we're doing, what we want to do, and then moving on to the first results. So showing you some of the images, some of the results of MeerKAT, some of the surprises as well that we've seen, and then moving on to Meerlicht, which is this optical telescope linked to MeerKAT. So that's the image of the MeerKAT array. And so the status of that at the moment is that there are 64 Gregorian offset antennas there. That was inaugurated in July last year. And there will be 3 receivers on these telescopes. The one that's in operation at the moment, which is marked in blue, is the L-band receiver, working from 0.9 to 1.7 gigahertz. But it will be extended to lower frequencies and later on to higher frequencies as well. So there's a very broad frequency coverage on MeerKAT over time. At the moment, we're working on 4,000 frequency channelizations, but this will increase to 32,000 channels, particularly useful for H1 measurements of nearby galaxies. It has an excellent instantaneous sensitivity, and in terms of the science that it's doing, it has 8 large survey projects, which takes about 65 to 70% of the time. And earlier this year, there was a call for open time proposals for the community to apply for time. And 38 open time proposals were awarded time, 16 hours each maximum in this first round. And in total, that's expected to ramp up to about 30% of the telescope time over the lifetime of MeerKAT. And as I mentioned, this is a pathway to SKA1 MID. But on that pathway, there's talk about adding 20 SKA antennas by the Max Planck Gesellschaft to build out towards the SKA. So just to highlight the impact this has on the continent, of course, as part of the African VLBI network, a communications dish was converted into a working radio telescope in Ghana. The opening there was July 2017 in Kutunze. There you see the antenna. And of course, this is the core of MeerKAT, which is down here in this particular picture. Okay, so these large surveys that Russ mentioned, I list them here. So there are 8 surveys, but they have various components. So MeerTime is a study of timing of pulsars, millisecond pulsars for gravitational wave work. Mongoose is a study of nearby galaxies in neutral hydrogen. This is a different component of MeerTime. The Duma is a very deep H1 study of galaxy evolution near the Chandra Deep Field South. We saw an image of the CDFS earlier with the AstroSat, but this is the MeerKAT equivalent of a deep field. The Fornex cluster, study of galaxy interactions in a cluster environment. TRAPPEM is to search for transients and pulsars with MeerKAT, and so on and so on. So the ThunderCat components here include cataclysmic variables, white dwarf accreting systems, short gamma ray bursts associated with merging neutron stars, supernovae 1A, and then X-ray binaries accreting black holes and neutron stars. It's the transient part, the imaging transient part of MeerKAT. There are timing domain transient surveys as well. And I'll talk a little bit about the commensal aspect in the second part of my talk later on. So in essence, we are looking at cosmic explosions, energetic outflows from these accreting systems, merging stars, but also anything that varies. And through the commensal part, which I'll discuss in a second, we will also explore the unknown, sort of looking at all the data to see if there's anything interesting that varies. I mentioned this is an international team of about 70 people, and Rob Fender at Oxford and myself are the PIs of this project. So for each of these teams, I want to highlight roughly the science case, why we're doing this, why doing this in the radio, for instance. So the cataclysmic variables, the white dwarf accreting systems, since about 8 or 9 years, these systems are known to be radio emitters. They're extremely faint in the radio, so that's 0.1 millijansky. But whenever there's an optical outburst, in this case of SS Cygni, a very canonical dwarf nova, we see radio flares at the beginning, at the start of the accretion onto the white dwarf, and recently also seeing radio flares at the end when the accretion switches off. And during the outburst, when the accretion disk in these systems experience a thermal viscous instability, it goes into a hot viscous state. The radio emission is persistently there, it varies quickly, and we really want to understand the nature of this particular kind of emission. It's faint, as I mentioned, and so we need a very sensitive telescope to probe this kind of emission. We're sampling nearby objects within typically 200, 300 parsecs for this particular component. X-ray binaries, there's some people in the audience who are very familiar with X-ray binaries. One thing we want to do here is to look at the X-ray radio relation in these systems when they go into outburst, to look at the disk jet coupling of these systems. So when they're in outburst and bright, they're up here. So that's the radio luminosity, and that's the X-ray luminosity. But we want to study them throughout an outburst, and particularly also in quiescence, how the X-ray luminosity, which is proxy for the accretion, links to the radio emission, which is proxy for the outflow in these systems. So the way we do this with Thundercat is we have a weekly monitoring slot where any system that's bright in an outburst will study for 15 minutes, short snapshots, together with SWIFT or other X-ray observations, and we build up a data set of about 1,000 observations simultaneously over 5 years of this particular work. And I'll show you some examples of where we are with this particular project. Then the very interesting, of course, gamma ray bursts associated, the short gamma ray bursts associated with the gravitational wave events and the type 1a supernovae. There, again, these are very faint. Typical levels are tens to maybe 100 microjansky in the radio. And here we need to trigger on an event and then follow the radio afterglow. And David this morning already mentioned the optical afterglow of 1708-17. This is an image of the radio afterglow of 1708-17. And you can see the time scale here. So it's almost observable for a whole year. Whereas in the optical, of course, the kilonova dropped out of the sky within a week. Here it peaks after half a year. And the green dots here are meerkat observations, contributing to the understanding of the radio afterglow, constraining the geometry of the outflow model using the radio data. So these are examples of what we want to do, but of course we want to be on Sky, and we've been on Sky for the last year with this particular project. And so I want to show you some results. Unfortunately, with the PDF, my animation doesn't work, so I've got a very nice animation that compares different observations of one particular X-ray binary, GX339-4. This was an observation taken with 16 antennas, and there in the center is the black hole X-ray binary. And the next image shows exactly the same image because it doesn't do the animation in PDF. If you want to see the animation, come and have a look on my laptop. But on the time when we started observing it with 64 antennas, it was gone. It wasn't there. So this was our first radio transient. It was there with 16 antennas, but not with the full 64. And that's just the system going through an outburst into quiescence. We've been following about 10 X-ray binaries now for the last year on this weekly monitoring. So here you can see the time covering almost a full year, in fact, a little bit over a full year. And the blue dots is in fact GX339-4. So when we first started observing, it was in a low state. And then, of course, it went to an outburst, and now it's currently again rising. So it's in another outburst. This particular object we'll study for 5 years. So we have a 5-year data set of this particular system, which is a wonderful legacy kind of project on that system. Other ones in this list, we target when they go into outburst. So they go into outburst and they decay. This one extremely bright, almost up to Jansky, and now it's decaying again. So there's a whole range of objects that we target, we follow, and of course simultaneously with the X-ray, so we can constrain the X-ray radio relation in these systems. One of the surprises, in fact, of these systems is that of the 10 or so X-ray binaries that we studied, 3 have shown extended arc-second scale jets, which is quite large, quite unusual. And there's MAXI 1820. Many people are familiar with that. These are meerkat images over a range of 20 days. And you can see the ejecta here, clearly resolved in the meerkat images. I should have said that with the L-band and an 8 kilometer baseline, the resolution we get with meerkat is about 6 arc seconds. Anyway, so this is a nice work. Paper has been submitted. 1820 is here. So initially it was coming down from an outburst, and currently it's brightening again as well. These are the names of all the people involved who take on one of these objects and study them. So Joe Bright was the student working on this, but there's a whole range of postdocs and students who take ownership of this. So even though it's a large project, there are clearly defined subcomponents where students run away with the data and work with it. Again, GX339, because we've got such an excellent coverage and we caught it initially in quiescence, we did a stacking experiment. We stacked 11 epochs and we measured radio flux in quiescence. So we can now extend this X-ray radioluminosity for GX339 for the first time really in quiescence. And again, try to understand the link between accretion and outflow, even when in the low accretion regime here. Okay. The nice thing of these data sets and the very large field of view of meerkats, which is about a degree on each side, is that you have the opportunity to detect other kinds of transients. So in the field of GX339 -4, we discovered a new radio transient. This is a nice collage of images. There you see the source, there it's not. And so this is our first commensally detected transient with the meerkat data. We did follow-up spectroscopy with SALT, thanks to David, and with Las Cumbres telescopes as well. It has a period of about 20-odd days, a K-type star, most likely an RCVN, although it's an unusual system. I see Dave sort of, it's a very unusual system in that regard. And we will expect to find many of these. This is just the first one that we discovered in our data set. And this is now being submitted. Cataclysmic variables, Albert, you might be interested here. So we did a nearby census of all the nova likes within 350 parsecs south of +10 degrees, 2 hours on source, and we've detected 5 out of 11 in the radio. These two, 603 Aquila and 3385 Sagittarius, are clearly detected, and they'll be subject to follow-up studies for variability and spectral index to try and understand the nature of the radio emission. And again, this is led by a master student in our group doing all this work. And a gamma ray burst as well, long gamma ray burst. We had to ask for director's discretionary time to follow this up. This was detected with MAGIC. It's a sub-TeV gamma ray burst, very high energies. And this is the meerkat radio light curve relative to the compact array. And this difference here is caused by the synchrotron self-absorption that happens in the early days of the outflow, the ejecta. So within a day, we were on target of this system. And I'll come back to this one in a little while, because it's actually a very interesting coincidence in relation to some of the other meerkat surveys. We have now followed up a second sub-TeV gamma ray burst, 1908-29A, which was detected by Hess, and is also followed up by meerkat. Okay, so Russ mentioned the petabyte data challenge. We've just had this monitoring program and a sample of 11 cataclysmic variables and a few snapshots here and there. And after 1 year of data, we're not at a petabyte, but we easily could have been, because we're not yet working at full channelization. So this could be a factor of 8 more, and we only have 8-second dump times, which could be a factor of 4 faster. 2 seconds is becoming the norm for doing this. So virtually multiply this with 30, and that's a more realistic number. So after 1 year, just Thundercat in this simple monitoring mode has accumulated 0.5 petabyte of data already. And because it's such a large team, we have, in fact, many of our colleagues working on the cloud, on IDEA or ILIFU. 24 Thundercat users are now using the cloud from all across the world. And it's a great way of giving access to such a large data volume. From our side, the opportunities are, of course, to create expertise in South Africa for our students and our postdocs to work with large, complex data sets, to create solutions for the SKA data flow, and to really start to analyze and disseminate the data quickly. And just to show, we've got about 9 ATLs, 2 papers published, 3 submitted, and 3 in preparation. So it really enables the science to be done, what Russ mentioned earlier, to have that facility to be able to reduce the data. Okay, so the discussion at one of the Thundercat meetings 7 years ago is, how do we characterize if you find a transient in your field? Russ showed a very nice deep image of the cosmos field, and there are lots of objects in there. So if you just find a transient there, you need the context, you need the multi-wavelength component. And very often with transients, they're gone before you can do the follow-up. So we wanted to have a telescope that wasn't responsive, but actually was always on the sky at the same place at the same time. And so to build our own telescope with the same field of view, a large field of view, 1.7 degrees on the side, we decided to build our own telescope and create a permanent link to the Meerkat observing schedule. Of course, only observing at night. You can't do this during the day in the optical, but at night you can. And so that really speaks to this commensal aspect. So one of the novel things of Meerkat is that as a transient search community, we are allowed to search all the data. And this also talks about Russ' points about data sharing, to search for transients. And it opens up the discovery space by a factor of 10 easily, just by being able to search all the data for new transients on different ranges of timescales, from a few seconds to a few weeks to a few days. Of course, we can't control the observing schedule for these surveys. We piggyback, we take the data off on the cadence that these other surveys are looking. But Laduma, for instance, will look at one field for 3,000 hours. That's an amazing resource to look for variability, both short-term and long-term. Mongoose will look at each galaxy that they have in their sample at 8 different epochs. So you can sample variability in those fields in the nearby galaxies on different timescales. And that's a great resource. On the timing side, there's a similar work being done by Ben Stuppers in Manchester and his group called MERTRAP, so transients and pulsars, with the aim to find fast radio bursts, very fast signals, the fast radio bursts at cosmological distances. Only very few are shown to be repeaters, so if you're not on sky at the same time with an optical telescope and you don't have the precision, it's very hard to find out where the emission is coming from. And again, the concept of having a telescope in the optical looking at the same field at the same time really will allow us to pinpoint host galaxies of fast radio bursts and other transient phenomena. So this is the Chandra Deep Field South and potential mighty fields. This is from the Meerkat Science book from 2016 that Russ edited. And there is one of our well-known cataclysmic variables, a magnetic system. And here is this gamma ray burst that I showed you the light curve of 190114C. It just happened to lie in one of the mighty fields, and it just happened to be observed 2 weeks before by mighty. And so we know that there's a host galaxy, and we know the host galaxy's emission from that as well. So the commensal aspect really has a lot of opportunities to find new and unusual transients in these fields. And so we've built a telescope, Meerlicht, 0.65 meter telescope, a 1 meter class, David, typically, a little bit less than that. with a large field of view and 0.56 arcsecond pixels. This reminded me of the talk earlier about the S Plus survey, which is 1.5 degrees and similar sort of pixel size, I think. But here we achieved that by a single chip. So a large STA chip, 110 megapixels. It's physically this sort of size, 10 by 10 centimeters almost, and a set of Sloan filters, including a Q filter, which is a wide filter encompassing G plus R. It's a broader filter. And within 1 minute of observations, which is our typical observing time, we go down to 21st magnitude in the Q band. And of course, with some of these fields, we'll be on sky for hours and hours, and we can do deep stacks and go much fainter. So the key thing, it's permanently tied to the MeerKAT observing schedule. We have no control over it other than where MeerKAT is pointing. So as I mentioned, this is again a collaboration of 6 universities or 6 institutes across 3 countries. And Paul Groot, who's in Radboud and Nijmegen, and myself are the PIs of this project. There's an image of Sutherland, and we've repurposed an old dome in Sutherland. Sure. An old dome in Sutherland where we now house Meerlicht. There's SALT for reference, and there's a whole range of other telescopes, LGOT. And what we're doing at the moment is to see also to link and develop VO event structures and the TOM LCO structures to link it to other telescopes so that we can trigger automatic alerts if we find an optical transient. The Data Intensive Astronomy Institute, ILIFO and IDEA, is very central in all of this. So MeerKAT determines where Meerlicht is looking. The data from MeerKAT comes to IDEA, but the data from the optical side also comes to IDEA. So from Sutherland, every image gets pushed to IDEA, to the cloud, and gets pushed through a pipeline. And so we have very rapid turnaround in the data analysis. And so there's data fusion going on at IDEA where we can trigger alerts in hopefully soon in near to real time. And so the idea of combining optical and radio really to do that simultaneously means that we have an always-on wide field of view synoptic survey, but the database is growing as well. So it's not quite the scale of LSST, but it's a big data problem to start to deal with that, and to data mine and to characterize and so on. Our typical sequence is 60-second exposures with Meerlicht in all the filters, but repeated often in the Q filter. So we have a 3-minute cadence, more or less, in this particular filter, so we can look for very short-term variability. Double white dwarf binaries, for instance, would be very nice to look at. And it reads out spectacularly fast, 7 seconds. I won't dwell on the pipeline for this, but just to say that this is all within the IDEA cloud. It's all containerized within the cloud, and all these components are working fine in terms of the database, the visualization, and the link then with alerts to the public. And you can also think of a citizen science sort of feedback loop in there as well. We haven't got that yet, but and so the turnaround here is just, the processing is basically, it can keep up in real time just depending on how many resources we put at it. This is a typical image from Meerlicht, one of the first light images. The moon is there for comparison to scale, and this is just the central region in the Milky Way, and that's one of the parts of the Fornax cluster. We saw this galaxy earlier on as well, 1365. And that's the typical field of view, 1.7 degrees on the sky, with amazing resolution. So the Meerlicht is now fully operational. The pipeline is fully operational. We've mapped all the known large survey project fields in all the filters. We've mapped all our own targeted sources. And we have had a number of dedicated campaigns, optical, radio, including SALT as well, which has been great. And we're doing a southern sky survey in the Q band to have a reference frame for gravitational wave events. So whenever an event goes off, we will have a reference frame in there. We'll probably extend this with G and R filters as well. But yeah, so that's ongoing, not yet there. And then within the cloud structure, we can do data fusion and do this multi-messenger, multi-wavelength coordination. one of the first things we've done is one of the MeerKAT initial fields, the MeerKAT deep field. In the radio, we've correlated with the Meerlicht image in the R-band magnitude. And so this is radio flux versus optical magnitudes. And if I go back to the picture on the right, you can see different sources in this optical versus radio flux distribution. X-ray binaries occupy this plane. Quasars, galaxies in this realm, supernovae here. But on this side, it's mostly stars and cataclysmic variables. So the very first sort of correlation of a 1 minute MeerKAT exposure with a short 1 minute Meerlicht exposure with a short MeerKAT image resulted in this particular correlation where you identify if a source is stellar or galaxy from the source extractor parameters in the optical, and then you look at the associated radio emission. And basically what we found is you can trace a population of presumably stars, bright in the optical, but excessively faint in the radio. So that's 10 microjansky here. So we can start to retrieve the faint stellar emission in these fields. And that's just a byproduct of doing these correlations. And that's something very exciting that we will work on. This picture really highlights to me the role of MeerKAT and Meerlicht together. So that's an image of Fornax A in the Fornax cluster with Meerlicht. And that's the radio overlaid, the MeerKAT radio image overlaid on that image. Looks a bit nicer in Keynote with the simulation, with the animation, but you get the picture. So that's the optical galaxy and the radio lobes beautifully around that. So on that note, I think these are my conclusions. I do want to say, and you can read the conclusion, I do want to say that Thundercat is very much an open project. If there are people who are interested in X-ray binary, CVs, short gamma ray bursts, and the supernovae, and you want to be part of Thundercat, just write a short motivation to Rob Fender and myself, and we've always accepted people on the project going forward. So if this is an opportunity to create closer ties in this particular field, I'm very open to welcome more colleagues on the Thundercat project. Thank you.
Hi. How do you organize the observations of, let's say, an antenna like the one of Ghana, which is somewhat distant, with the South African array? Do you do VLBI? Or?
I personally don't do VLBI, but there are people within the MeerKAT community who are specializing in VLBI. And certainly the aim is that the Ghana antenna is incorporated within the global VLBI network. And certainly for these kinds of objects, the X-ray binaries, when you see these ejecta, it's very useful to go at higher resolution to see higher angular resolution ejecta evolving over time. But personally, I haven't yet incorporated the Ghana telescope with our science, but I know it's part of the drive to convert more of these antennas across the continent to create the necessary baselines for the global VLBI. Yeah, so in principle, I mean, when they launched it in July 2017, it demonstrated it was connected to the VLBI network. So that's.
Patrick, I have a question about SS Cygni.
Yes.
Do you see the second peak at the end of outbursts each time?
Yeah. So this is a new thing. It didn't show up in that image that I showed you there, but SS Cygni very repeatedly goes into outburst in radio when the optical outburst happens, and from more detailed coverage now. It seems that almost every time if you cover that phase right, there's a bright radio flare at the end. And I think it's when the accretion switches off. In VW Hydri, we think that is associated with a sort of shutdown of accretion, and maybe some propellering is happening of material. I'm not sure if that's the same in SS Cygni, but...
Okay, thank you.
Yeah.
I've got two questions. First one, considering the faintness of radio emission from CVs, what is a reasonable time resolution you can achieve having a decent signal-to-noise ratio?
Yeah, so we've covered these systems for 2 hours, basically, which is often an orbital period or thereabouts. We can divide it up into 15-minute blocks, and you still get reasonable signal, certainly for the two brighter ones. But some are extremely faint, and you just need to integrate for 2 hours. So it's very hard yet at this stage to get a sort of binary coverage or that kind of thing. We will follow this up now with Meerkat for these two systems for 4 hours, and sort of try to get a higher signal-to-noise.
Okay, that's one question. The other one, the Meerlicht is is an instrument which does imaging and different filters. Is it planned to expand this follow-up observations also to spectroscopy?
So at this stage, we just match photometrically the entire field of view, so that we can issue triggers to the 1.9 meter in Sutherland or the SALT telescope. And we've certainly had coordinated spectroscopic runs. If we had a dedicated target on NewSat 4, for instance, the magnetic system, we observed it in the radio, and Steve and David observed it in SALT with spectropolarimetry as well. The one interesting expansion in the future would be near-infrared, maybe to get a wide-field near-infrared imager who can at times coast there with the optical.
Yeah, thanks for your talk, very nice. I was going to ask something related to that, but so you already answered that. I was just curious. Did you, when you say you built the telescope, did you actually build it?
I didn't personally build it.
No, yeah. I mean, you in the plural.
Yeah.
I mean, was it built in South Africa? Or?
It was. So the collaboration is between South Africa, the Netherlands, and the UK. It's the optical group at Astron in the Netherlands who designed the telescope. And the design there was then optimized to get a large field of view at reasonable resolution. Yeah. Thanks.
A couple of other transit type of objects in addition to compact binaries. Are you looking for tidal disruption events? You haven't mentioned them in the talk, so I was curious. And two, have you detected any fast radio burst, or is the field of view probably not large enough to give you a chance for that?
So those are two very interesting questions. So in our original Thundercat science case, tidal disruption events were there, as were ultraluminous X-ray binaries. But in the 2016 review, science review, those themes were deemed not exciting enough. So we were left with these 4 particular themes. We will find them commensally, I'm sure, when you look at all the data. Some of these transients might be associated with tidal disruption events in galaxies far away. As to your second question about fast radio bursts, in fact, only 2 weeks ago was there a dedicated campaign with the Meertrap pipeline on the repeating FRB that was detected by Arecibo at plus 33 degrees north, and they detected 12 bursts in 2 hours. It's currently in a very active state. But it detected in timing 12 rapid bursts, and we also took imaging data as part of this commensal. So the telescope can do timing and imaging at the same time. And that's still being analyzed at the moment to see if we can see anything in fast imaging as well.
Okay. In the list you have shown with 18 different projects, okay. How are they coordinated concerning to the different sources? I mean, each project is going to be observing different sources, or are there redundancies?
So there is not a full sky survey to be done with Meerkat, as far as I know, certainly not planned at the moment, but the different large legacy teams each have different objectives. So MIGHTY, which is the project that Russ is leading, will sample a number of fields, number of areas quite deep to look for galaxy evolution, deep continuum imaging, polarization of sources. Sorry? Faint stars. and so they have predefined areas on the sky where they look. Mongoose will look at 30 nearby galaxies, and that sample has been set. It's fixed. And the Laduma is one field, the Chandra Deep Field South. That's just one field where they look at for redshifted H1 of mission.
Thank you.
And just a quick question from me. So that comment, so transient that you showed, how did you find it? Was it by human inspection, or there was something clever already going on there?
It was still by human inspection. We had a workshop in December last year where we looked into the data. We ran all the sources to the transient pipeline, and there are parameters there that tell you if a source is variable. So we picked it up from the output from the transient pipeline and then followed it up. And of course, we have now 5 years to study this source in detail. But yeah, so the aim is that with these correlations, with this optical radio correlation in real time, to develop tools, machine learning tools that will allow us to distinguish very quickly if it's a star or a galaxy or what it will be. Good.
Well, lots of questions there. Thank you very much.
Great pleasure.
And now we have another radio talk. Jacques.
Thank you.
So, let's see.
Is the sound okay? Good.
Yes. Thank you.
Cadê o... Okay. Well, I am going to talk about several things. The Llama project, which is an antenna in the Andes at a high frequency that we are constructing. Let's say, we submitted a proposal to the BRICS, and I understood that I had to justify why we did this proposal. So I will explain, let's say, the BRICS connection with Llama, and then I will talk a little about also an array of antennas in Latin America that is starting now too. So let me understand how this works. Okay. So this is the summary. It's a 3 parts presentation, let's say. So this is the Llama project. There is a list of people, but just to show that, let's say, we have some 15 people, mainly from the University of São Paulo, from my institute, which is the Astronomy Institute, but there are some people from the Polytechnica School, which is an engineering school, and there are people from other institutions, let's say Mackenzie University, which is a private university but has a group of radio astronomers there, and INPE, and we have some collaborators. I like to put the first name is Thijs de Grauw, who was the former director of ALMA project, and he has collaborated a lot with us. He came very often to São Paulo and also to Argentina, because it is a joint project, Brazil-Argentina, and he's helping us a lot. So, Llama will look like this. This is the Apex radio telescope, which is situated close to the ALMA site at 5,000 meters altitude. Our antenna is at 4,800 meters, so not so different in altitude. It is made by the same company, Vertex company, which made a large part of the ALMA dishes and made this Apex. This is a little different from the ALMA dishes because it has two cabins, Nasmith cabins on each side. And we also have made the option of having a Nasmith cabin. So this was the situation of the place where the telescope was going to be built, so some few years ago. And this is the situation today. You can see, let's say, there is a good road to go to the mountain. This has been made plain, but let's say the antenna is there. It has been already constructed, but it is in the containers because we had some difficulties from the financial point of view from our partners, let's say. The situation is not easy in Brazil or not easy in Argentina, and we had to wait. There is a whole something like I don't. I am in the wrong. Okay, here where we are going to build a concrete base and mount the antenna on the top of it. But let's say we have been. Something more. We have a site, let's say, operation center in the small city of San Antonio de los Cobles, which is 3,800 meters altitude. So it's a place where we can, let's say, operate because we cannot live at something like 5,000 meters altitude. We can stay for a short time and then we have to go back. So the radio telescope will be operated at a distance. So just to tell you about the difficulties that we had no director responsible for the project because let's say the first director resigned when the second who appeared became sick and many problems. So we also had no funding, no progress in the construction of the base. And this is written in Portuguese, sorry. It is telling that our foundation in São Paulo State interacted with the ministry in Argentina to get the things running, and it is okay now. After August this year, a new guy, Alberto Echegoyen, an important scientist who was responsible for the installation of, let's say, the Pierre Roger cosmic ray observatory in Argentina, is starting to work as the guy responsible for the Llama project on the Argentinian side. And Llama now is going to share the site with Cubics, which is another, it is a cosmology program, French, Italian, Argentinian, and this instrument will be installed at less than 1 kilometer, so that we share, let's say, the road and the infrastructure. More importantly, that let's say, the energy supply system, we decided to take it from gas, because there is a gas duct passing close to that, and we are going to construct. We are starting, let's say, this construction of the gas turbine energy feeding system. There is a new board of directors, completely new from the Argentinian side. The joint power plant is beginning, and they will share also a mechanical lab and electronic lab in Salta city. Salta is a relatively big city, 300,000 population. There is university. It's a good place to stay, and it is only 2.5 hours by car from the Llama site. I will skip this. It's just to say that, let's say, the board of directors have changed, but you don't have to know all these names. What is the scientific aims of the Llama radio telescope? Well, solar radio astronomy, because the dish is such that you can point to the sun. The sun, the visible light is scattered, but not the radio light. And so astrochemistry, we have been working in astrochemistry with a group, let's say, interested in discovering new molecules and seeing how these molecules can, let's say, indicate the physical conditions in the star-forming regions and also in envelopes of AGB stars. And we can, let's say, investigate extragalactic megamasers, evolution of galaxies, variability of nuclei, because, let's say, some of these extragalactic nuclei have let's say, a not so steep decrease in power with the frequency, so that and let's say very long base interferometry. We want to be part of this EHT collaboration. And you have seen, let's say, the image of the black hole, which appeared very recently. This kind of study, we want to be a part of this. So, this to give an idea of a radio telescope. The dish is here. There is a Cassegrain cabin, and there are two Nasmyth cabins. So, a set of mirrors send the lights here to the cryostat. And let's say we will have two cryostats with room for 3 receivers in each one. But we are going to start our life with only one cryostat and with two receivers, let's say. The 2 receivers are presently, they are constructed, they are working, and they are in the NOVA laboratories in Holland. Let's say we have this collaboration with the Groningen group. So this is to illustrate the parts, mechanical parts, but the dish is here, so this system with all the mirrors. Here there is a system to put, let's say, the calibration charge in front of the receivers. And there is a system to inside. This crosses let's say through the axis of the telescope, and here is the cryostat, and it is a system that we can easily raise it to make the maintenance of the helium cooling system. So these are the details of the system that you can raise here, and so that you raise the cryostat, the system which goes in the Nasmyth cabin. So just to give you an idea of what is this, and the pieces that you have seen in computer drawing, now you can see them, let's say, being already constructed. This is the big piece which goes behind the let's say, the dish, and this is the system which is for lifting the cryostat. This happens in a company in the interiors of São Paulo State, a city called Araraquara, where we found a mechanical company who agreed to do this, let's say. And so we are going to have a spectrometer made of many modules of fast Fourier transform analyzers. We have, let's say, IF prototype. This was going to be a prototype, but at the end, since the crisis is so big, it is not going to be a prototype. We are going to start using it, but it has been tested, it works, it is very stable from the thermal point of view. So this is the group in NOVA, and here we have 2 engineers that are from São Paulo, from the Polytechnica School, 1 engineer who is from Argentina group, and let's say this is Andrei Barishev. I am going to talk about him because he is the head of the lab of terahertz lab in Nova. And some details, let's say, but we are taking care of it. When the telescope is installed, the first thing that we have to do is to check the pointing all over the sky, and we do this with in the optical, let's say. So we have a telescope with a camera and all the, let's say, computer system to compute exactly what is the displacement of the optical sources. Of course, there are sources which are both radio and optical, like Jupiter, for instance, and some others. So we can make the connection, but it is much easier to find the errors with an optical system than with a radio system. And this is, let's say, a holography receiver, because the panels of our dish are very precise. It is 10 microns RMS. But we want to have a final parabola with 20 microns RMS. So we have to adjust the panels. And this we send a signal from a tower, like it is done in Alma, let's say, from a tower 300 meters from there. Then this wave is reflected by the dish and comes to the receiver. The same receiver sees also the signal coming from the other side, from the receiver. And it makes a phase comparison, and you get a picture of what is wrong, let's say the quality of the mirror, and then you can go and adjust each panel. And it is not the only way of adjusting panel, but it is what we have chosen. But this belongs to NRO, and they agreed to, let's say, to give it to us for 1 year, only 1 year. So we have to compute exactly when the antenna will be ready for this, to do these experiments. But the transmitter, they could not give because they have used for other things. So we are building the transmitter at 104 gigahertz in São Paulo. So now, why we are in the BRICS project? Because we need superconducting terahertz receivers, and the Russian groups are developing this for ground-based, but also for the millimetron radio telescope that they plan to put in space. Thijs de Grauw, I talked about him. He is involved also as in this millimetron radio telescope. So to have good receivers at these frequencies, we have to have this to advance in sub-terahertz technology. And the BRICS members have strong, let's say, work and tradition in radio astronomy. And the millimetron observatory with a 10-meter space telescope, which is a successor of a radio telescope that is operating in Russia, they also probably will need some ground-based radio telescope at the same frequency to make the LBI from space to the ground. So we are collaborating for these reasons. So who are the persons that are involved in the project that we submitted? And we don't know yet the result, let's say, of our submission. The leader of the project is Valéry Kocholets. He's from the Kortnesnikov Institute of Radio Engineering and Electronics. Sorry, Natalia. Yeah, but I learned from Natalia that, let's say, there is also another group in Nizhny Novgorod who is interested in doing these tiny components, SIS, superconductor, insulating superconductor. They're very, very small. But let's say he does Valerie, what we consider the best ones, but he has not the system to test it. And this is why we have also this collaboration with Holland and Andrei Barishev, who is the director of this group. They put these components in receivers and test them. Our group from São Paulo is sending a student, a PhD student for 1 year there. She is going now in next month to work because she likes high frequencies, terahertz technology. She's not an astronomer, let's say. And so this collaboration is going already. From South Africa, we let's say, have a collaboration with Conrad Fourier. He looks like a French guy, no, Fourier, Fourier transform. But he is constructing, I will show what he's constructing, parametric amplifiers. And this is important because, let's say, we have the high frequency part of the receiver, but then we have the IF frequencies. 5 minutes. Oh, well, I go. I skipped our Chinese collaboration who are being won. Okay, so Brazil, what is the collaboration of Brazil in this? Is having the Llama project, let's say, a place where you can test receivers and see if it is okay, measure the antenna temperatures that you get. And South Africa is developing these Josephson traveling wave parametric amplifiers, which are very, very low noise. Now, I will talk a little about the EVIA. It is a totally different project, but we have seen that there are these kind of dishes that were used for telecommunications in the past. We have some of them in Brazil, but there are in Peru, Ecuador, Colombia, Mexico, Costa Rica. So we were strongly influenced by the Ghana experiment. The Ghana radio astronomer, he became a radio astronomer, was there in a meeting in Mexico where all this group was there, and we decided to do the same. And so just to show you, this is the antenna of Sicaya in Peru. These two antennas are in Brazil, not far from São Paulo. So it is Morungaba antennas, and this is the place of the antenna in Colombia. But let's say this is the antenna in Uruguay. Uruguay at the beginning was not in this list of persons, but they discovered the antenna and they are already testing it. And so this is the antenna, the 32 meters antenna in Mexico, because our meeting was in Mexico. So we visited the system, and you see it is quite high place, but I succeeded to go there and walk on the antenna. And this is a view of Tangua in Rio de Janeiro state. And so there is another antenna here that we don't see, but I will show it to you. So this is the list of the people from South America, but also there are people involved from Spain and Portugal. This is why we are calling this Ibero-American effort. and all these people sign a document saying, well, this is the initiative, we are going to do that. So each of us come back to his country, and the first task is to go to the place, talk with the company which is owning the antennas, and see the situation of the antennas. This was, let's say, the meeting in Mexico. This was a regional VLBI meeting, let's say. And so these are all people. This is Patrick Colomer. He lives in Netherlands. He's responsible for the VLBI network. This is from Ecuador, from Costa Rica, from Peru, from Argentina. And so there is some science cases for single dish observations, radio continuum flux, pulsar observation, emission line spectroscopy, because let's say there are methanol measures. But I have to go fast. A science case for VLBI observation, so mapping interstellar measure, distance of star-forming regions in the Milky Way, let's say, to trace the position of the spiral arms is very interesting. Active nuclei, and searching for radio transients. Now, after the talk of Patrick, I see that we have a lot of common activities, let's say, and it is perfectly natural to have a collaboration. So the first actions in Brazil was to visit the Tangua antenna, which is 50 kilometers from here, very, very, very close. And so the first stage of the project is to use the antenna as a single dish. And we were planning to make a receiver from 4 to 8 gigahertz. But now, after your talk, I think that we should shift a little lower frequency to, let's say, to be able to make some VLBI experiments in the future together with South Africa. And so this is, let's say, the antenna in Tangua. It looks dirty, but this is not a problem because, let's say, the Mexican antenna was dirty like this, and they just washed it with soap and water, and it became clean. So the antenna obviously has some problems, some rust, but it is nothing fundamental, which is a very bad problem. So this Tangua antenna is usable. This is the team which was there for the inspection. So this guy is from the Mackenzie University. She's from the MAST. This is me. This guy is the vice director of Observatório Nacional, an Institute of Astronomy of Rio here. Because let's say we were trying to stimulate the people from Rio, because I believe that this was the best antenna. And let's say from São Paulo, it is not too far. It's some 400 kilometers. We came by bus from there to here because, let's say, we have no funding. For the moment, we don't have money. We just work with like we are. And so this is so future VLBI with South Africa and maybe BRICS. We should do that. Let's say all the list of science cases that you have put it is an enormous amount of science cases. So there is room for collaboration, and we should do that. Great.
So that was an interesting proposal for starting some radio network among ourselves. And are there any questions? Yes.
Yeah, so the name of the antenna is the millimeter array. Are you planning to have more than one antenna for Llama?
Yeah, at the beginning we were thinking of yes, I have a microphone, so I don't need. At the beginning we were thinking that it would be nice to have 2 or 3, but let's say by the situation of the funds now it is only 1 antenna. It is close to Alma. It is 180 kilometers from Alma. There is the frontier between Chile and Argentina, and there is a road, and there is even a fiber optic system which is being installed to go from Chile to Argentina. So we can do VLBI also with Apex and some other antennas there. And but if in the far future we become richer again, we can put more antennas. But the name, yes, large Latin American millimetric array for the moment is incorrect. Yeah.
Jacques, I just want to mention that for millimeter and sub-millimeter wave receivers, there's also a very strong group in the Purple Mountain Observatory in the same city as the university, Nanjing University. In the same city, the Purple Mountain Observatory has
as I told you, we are interested in having more partners because the teams are small. Let's say a lot of work to do, and let's say only the computation part is we have to control the radio telescope. Let's say everything: receivers, frequency, spectrograph, data acquisition, movement of the antenna, and all the but to be done remotely. So it is a big problem, and for the moment exactly, we have a collaboration from a postdoc from Netherlands. By Skype, he helped us, but we have in São Paulo 1 engineer only working on that. It is. I think that we are going to, if we continue this way, to arrive at the moment of observations. And well, very basic activities will be okay, but no more than that. So yes, we need to have more collaboration, and we have to talk about this.
Well, the deputy director of Purple Mountain is attending this meeting. He's not here now, but he's here, so maybe you can can talk to him.
Yeah, I met him yesterday. Yeah, okay. But tomorrow he's probably going to be there. I don't know.
Yeah. So I think this is certainly something for us to keep an eye on for the future developments.
Ulysses is involved in this EVIA project.
Marginally.
Yeah. He will be the guy who will take care of the data handling and sharing.
Once the data is flowing, yes. Before data is flowing, no. Okay, so there is a question.
Okay, thank you.
Jacques, just coming back to Llama, how late Llama is concerned to the original schedule? How late?
How late it is? It is difficult to say, but during 1 year we were almost stopped, let's say. But it is more than 1 year. It is, since if you consider from the very beginning, because it took time to build the road, it took time to do a lot of things, I would say that it is 2 years old, late, yeah. Yeah.
Okay, so thank you, Jacques. Thank you very much. And now we have the coffee break. So on the same place of the coffee break this morning.
Vários projetos.
Isso outro apareceu.
tem que tentar, né, Jacques?
De graça.
Pois é, exatamente.
Vai prestar para o Steve.
Antônio Mário.
Gostaria de chamar aqui na frente o Dr. Antônio Mário Magalhães, da USP, para falar sua palestra.
Para retirar o prêmio da rifa. Okay, so we continue with the instrumentation talks, and the next one given by Antônio Mário Magalhães from IAG at the University of São Paulo. Did you let's switch on? Okay, just hold, press and hold. Oh, there you are. Okay.
Yes, it's working. Okay, thank you. All right.
Okay.
Thank you. Thank you.
Thank you very much.
Well, thank you. Oh, that's the okay. Okay, good. Thank you. Well, first of all, thanks Bruno, Ulysses, and Patricia, and everyone else who made the meeting possible. This is my first BRICS meeting, so I'm learning a lot. I've never been to one of them earlier, so I'm learning a lot. I'm listening more than talking. So it's been a good experience, and I'm learning a lot. So this project has been funded by FAPESP. That's the instrument that we built with people here. You may recognize some of the names. I guess I have to put this even closer here. Okay, let's try that. Okay. That's Claudia Rodriguez works with symbiotics in interstellar medium as well. Marcos Diaz with Novi, Reynaldo interstellar medium. Pereira's works with interstellar medium as well, and then stellar envelopes. People who helped us develop the software. Of course, we always programmed in Fortran, before any of you were born. So, but these people translate into more normal languages. And then, yes. Okay, good. We collaborate with some other people, and I want to mention people who actually built the instrument, mechanics, did the design and built the instrument. Firmino, Jacques mentioned him. Looked like it was on purpose, but I was going to mention him as well. And people from Radboud and Hiroshima in Japan. Okay, so this is the layout of the talk. A little introduction, of course. Talk what does South Pole mean? The polarimeter we built, and we have some commissioning data. I'm going to talk about that. See, and then you can. So it's always nice to give to give a feeling to people what the instrument is able to do. And then, the science of the instrument, that to be able to do with the instrument. Yeah, okay. So I'm going to spend a few minutes just talking. I think it's interesting since it's a little informal to some extent meeting. People, this is a former student, Claudia Rodriguez, working with cataclysmic binaries and ISM. Claudia is also doing polarimetry. This is the Spark 4 instrument that's going to be sitting at the LNA observatory. So it's a 4-channel polarimeter, imaging polarimeter. So that's going to be very interesting to do, to use. This is Carlos Firmino, who actually built our instrument, or the electronics, the control for the instrument. As Jacques mentioned, there's in the state of São Paulo several small businesses developed that they can do very high-tech stuff. So this guy, particularly Carlos Eduardo, he worked in addition to our instrument, worked with the JPAS or the survey that Ariane mentioned this morning. Worked for the CTA array in Italy, the Llamma telescope, as Jacques mentioned. So In fact, just since I am, we are from São Paulo and Rio, so I'm going to mention that something that came up. It's nice to see how the other people look at, at us in general, people who have nothing to do with science, like, Financial Times, right? So they put São Paulo among the Latin American states, of the future. Rio didn't fare well, didn't fare poorly, either fairly very well. So, okay. Many cities in Chile and Argentina as well. So to prove that you may have hair, at some point in your life. This is a 1980 picture where we had our first polarimeter at LNA, the unidimensional detector, right, which is a photoelectric polarimeter. But still, now a CCD version of the polarimeter is very much in use now. It's among the most used instruments at LNA. And more than 30 theses, in the past couple of decades have been done with it. So it's nice because, of course, Brazilian weather doesn't quite compare with Chile. So we built an instrument that can accommodate, observing under less than ideal weather. Okay, so that's the original instrument that we built at LNA. So it's essentially CCD with a filter. That's your imaging part. And then you put the polarizer wheel and then the rotating wave plate retard. I don't want to give details, not to bore you very much, but just so that you have an idea. Okay, so the idea is to measure polarization. Why do we measure polarization after all? Why in the hell we do that? And that's the reason is that physics, it gives us information, of course, about physical processes in the source and between the source and observer, essentially about symmetry, as we will see in a few examples that I'm going to tell you about. So many processes, this is a short list of processes that originate optical or near-infrared polarized light. Some of them go into the radio, some of them go to the UV as well, but I'm talking about optical near-infrared. The scattering, as you know, Thomson scattering was mentioned here, synchrotron radiation, cyclotron radiation, cataclysmic binaries, it's a complete astrophysics there when you talk about polarized light. So polarized light is interesting. We are throwing away information if we just measure the intensity or the spectrum. Oh, another example is just the recent Planck data. This is a combination of several channels and the Planck data of the whole sky. Planck wants to measure the CMB, of course, cosmic microwave background. But of course, there's something between us and the CMB, which is the galaxy. And of course, the galaxy is polarized, right? So if you want to measure if you remember, one of the goals of measuring the CMB is to measure CMB polarization, because that will give you information of the first instance of the universe. But of course, you have to, deal with how to use that, take that foreground into account. So this is where, some of the what we do plays a role. Anyway, the polarization is caused, if you're curious, by aligned grains in the magnetic field of the galaxy. So I'm going to be quick here. I can give you more details if anyone can raise their hand. But also, for instance, if you want to observe stellar envelopes, picture if you have a Tauri star or a BE star, and you observe the direct light from the star and light scattered from the envelope. If you look at the envelope from above, this is going to have some circular symmetry, if you want. It's going to be symmetrical. So the polarization seen from above will be 0 from scattering. But if you look at the system from the edge, as an edge on, and then you see a net polarization because it won't be canceling here. So there's a net polarization. That gives you the inclination of the disk, for instance, and more information. Okay. So anyway, despite all this motivation, there's someone said in a Madison meeting on polarization that polarization is currently the last frontier, the final frontier, right? Because it hasn't been done. We've heard a lot of talks, very good talks on the radio this morning and this afternoon. And the radio polarization is built in, right? Because you measure that, essentially. Unless you go to high frequencies, then you have to put some polarizers. But in the optical, of course, you have to put some optical pieces if you want to get some polarization. So the survey that we envisage should provide, tens of millions, if not more, objects. Anyway, so what is South Pole? That's what we are working here. So where is South Pole? Oh, South Pole is an optical survey of the southern sky. The goal is to measure every star that, up to minus 15 to begin with, to 0.1%. This will be like 0.001 magnitudes, for instance, if you're into magnitudes at V equals 15. So that's the original area of the sky that we would like to measure from the southern pole, southern equatorial pole to about minus 15. So we get the Magellanic Clouds, zones where the CMB is important, the galactic disk, and so forth. So to give you an idea of the accuracy, for the telescope that we commissioned the instrument with, which is the T80 telescope, so 15th magnitude, and we aim at for a 45-minute integration, 0.1%. But of course, if you look here, we can reach 18th or 19th magnitude with about let's say % accuracy, which is good, for instance, for blazars, things like blazars, for instance, if you're into that. So we built the instrument. This is about 60, 70 centimeters across. There's a rotating wave plate, a polarizer wheel, and then a filter wheel as well here. The filters are all this big. Since the filters have to be big, all the elements are actually mosaic. So nature doesn't give you a nice calcite block this big, so we have to build like in a mosaic. So it was very, very, very interesting, very challenging, but it was interesting. So that's the instrument built in. Okay, the way you measure polarization, one of the ways to measure polarization in the optical is usually expressed about the Stokes parameters, Q and U. That's the linear part of the polarization. The Q parameter is just the difference. It's like you took your polarized sunglasses, right, and you measure the intensity of light in one position and 90 degrees apart. That gives you, for instance, the Q parameter. And if you do the same at 45 degrees and 135 degrees, that difference in flux is the U parameter. Okay, so the commissioning data, well, we heard about the T80 telescope earlier this morning by Yanni. So that's where we commissioned the instrument. This is Claudia, and there's people from S+, that help us with the instrument. This is it's a similar CCD that Patrick just mentioned. It's an EV 10 centimeter across chip. It was a little challenge to do the reduction with it. We didn't know it. We were not familiar with that. So what we want, by the way, the calcite block gives you two perpendicularly polarized images. This is how you get the polarization. So this is the raw image, and you want to have a nice image where the stars have the vectors, the polarization vectors, right? Where give you an idea of the polarization, right? Okay, so we built a pipeline for that, and then we just built a Python script to run the pipeline. So everything you can throw a night's complete, a year worth of data, and the thing will digest it. So that's good. So the commissioning data indicated that we are measuring, previously measured stars very well. Well, let's say with good precision. Precision was good. Precision is good. That's this data that we had. Let me go back a little bit. Was just 4 integrations of 10 seconds each at a given wave plate position, right? So only 40 seconds per wave plate position. So that's the polarization versus magnitude in that particular field that I'm talking about. Of course, polarization. There's a statistical. There are two factors here. The polarization. If you look farther away, the ISM will polarize more the stars. But of course, there's a statistical influence as you go down in magnitude. Polarization is a definite
positive definite quantity, so there's some bias there. But anyway. But the important thing is to look at the error in the polarization versus magnitude. So if you take the 15th magnitude value that we were talking about, we get here the sigma, the error of the polarization of 0.25%, right? And if you scale down to what we had a table for, a 5-minute integration per wave plate, it's 0.1% essentially, which is exactly what we expected. Now, we haven't even flattened, flat filled this data, not corrected for bias or anything, just the raw data, and ran the pipeline, and it gives you the photo noise limited data. So it's comforting anyway. So what's the status of it is performed according to specs. It's photo noise limited. Pipeline is built and is Python, if you like Python, if you like Fortran, if you like Python, it's working fine in Jupyter. So the nice thing is that, well, I think it's a nice thing. We will upgrade, the intention is to upgrade the polarimeter to have a spectroscopic and spectropolarimetric mode. Okay? So you can, if something, if something bursts in the universe, we can point the telescope, put it in the middle of the chip, and then put a mirror and send to a low dispersion spectrograph and measure the polarization of it. So of course now we originally, a couple of years ago when we built the instrument, the idea was to use the T80 telescope to use it, to use the instrument and do the survey. But yeah, it wouldn't work out. We couldn't agree with the PI of the instrument, and so so we are actually negotiating with the observatories in Chile to have a telescope for the instrument. Usually it's the other way around. You have the telescope and build the instrument. Now we're doing the other way around. So anyway, I may have more news in a couple of weeks, a couple of months, hopefully. Okay, so let me talk about some of the astrophysics that we think South Pole will be good for. This is the CMB. Okay, this is frequency. This is high frequency. Oh, this is low frequency, high radio frequency. So this is dust emission, like this dark red here is dust emission, and this is synchrotron. This is the galaxy foreground, right? And that's the CMB. So there's no problem. If you look at the intensity of the CMB versus the foreground of the galaxy, there's no problem, right? You can more or less easily measure it. But when you look at the polarization, typical polarization signal in the CMB, and you have the polarization foreground of the galaxy in synchrotron and dust, then it becomes a problem, right? So this is why, for instance, in the CMB field that the BICEP 2 pointed to, apparently there were some of those B-mode polarizations in the CMB, but of course later there was the issue that they were really actually there was slight contamination of galactic foreground. So you really have to measure those fields with accuracy. That's what we think the South Pole will be important for. Observing the CMB fields to get the actual polarization. By the way, I didn't mention it. I should have. When you look in the optical and you measure the magnetic field, right, or the foreground, that's going to be the same polarization as in the high frequency radio domain, right? Because it's just the you have the grain, right? You have a magnetic field. Yeah, the grain is rotating like this. The field is like that. So when you have a background star in the optical, right, you observe more here than here. So that's going to be polarized with the direction of the magnetic field. If you look in the far infrared or submillimeter, of course, this grain is going to be emitting. So it's going to be, the light is going to be more light coming this way than this way. And then the emission will be 90 degrees from the optical absorption. So it's going to be the same, essentially the same. So you can translate from the optical to the to the submillimeter, the polarization that you measure in the optical. So anyway, I'm going to give you some, we did an initial survey of the polarization, interstellar polarization at LNA. So we have measured high latitude, latitude fields. We have measurement for those. We are going to make them public as soon as we finish reducing them. We are doing with Marijke Haverkorn in the Netherlands. We are doing this in collaboration with her. So extragalactic, if you don't like CMB, you can use South Pole data for extragalactic astronomy. Blazars will certainly be discovered. Most of the Egret and Fermi gamma ray sources are blazars. So those are going to be showing up in a South Pole survey. Optical counterparts of gravitational wave events. We heard the talk today was great about the electromagnetic emission from these merging events. And for instance, the neutron star black hole mergers are supposed to give even more asymmetrical ejecta than, for instance, the neutron star situations, for instance. So that's would be nice to use that spectral polarimetric mode for. Okay, let me skip this. So the data is observing the whole available sky for polarization should be able to give us magnetic field influence on the evolution of molecular clouds, on plane alignment theory, and magnetic field structure of the galaxy, because now we have parallax from Gaia. For instance, this is the Matthew Swanford map of the polarization of the ISM, okay, looking at the whole sky. Well, almost the whole sky, but the whole plane. So, of course, we just had a 2D dimension, 2D picture of the polarization. Now we have Gaia, so we can invert the polarization, right, and get the magnetic field structure of the whole galaxy. That's gonna. We started coding that, so that's gonna be interesting as well. So, but anyway, anyone can take the data later on and do that. The other influence that I was talking about, molecular clouds, that only polarimetry, mostly polarimetry can give you. For instance, this is the Musca dark cloud. This is about 3 degree field, 3 degrees by 3 degrees. Musca is in the southern Milky Way, for those who like to picture, right? I always tell my students, when I discuss Centaurus A, synchrotron, etc. And so, this galaxy is in the sky. You have to look at the right place. You can make a picture with your 500 millimeter lens if you want. Anyway, so that's a cloud, that's a dark cloud, right? This is dust hanging in the sky. And why does it have that shape, right? And if you do the polarization, if you measure the polarization of the background stars through the cloud, and then you see that the background stars give all the polarization like that, meaning that's the direction of the magnetic field projected on the sky, which means the cloud is collapsing like a pancake. So the magnetic field is very important for the cloud evolution. It tells the cloud how to evolve. Right? The green is optical, and this is near infrared that we measure at H band. So stellar astrophysics also, as we heard about, white dwarf, magnetic white dwarfs within the cataclysmic minors, GRBs and supernovae. Of course, we have data from LNA. I didn't put here because it'll be too long. I have some papers on that. And this is a particularly interesting aspect, studying the circumstellar environments of evolved, either young stellar objects or evolved objects. But young stellar objects are like, Titari stars or Herbig-Hauer stars. Okay, this is within the survey of. This is Claudia Rodriguez' work with us. This is a Herbig AB object here that we measure the polarization for. And here, this is the same object which has been observed with AO, adaptive optics, right, I think it was the Palomar telescope. And there are two vectors here, right? Two orientations, right? One is this is the picture of the object seen edge on, right? So there's the absorption band. The red, it doesn't appear here, but the red is the outflow, direction of the outflow, and the black is the polarization, okay? That we measured. So the polarization does give you the orientation of the envelope of the star. Of course, here we see the AO, but of course in this star we don't see, maybe the star is too small, it doesn't show up, and other places we can say that really polarization of Herbig AB objects gives you the orientation of the of the information on the envelope, right? So and of course, you know, I'm extrapolating a little bit here. Even so, oh yeah, let me. Okay, I skipped that slide because I thought I wouldn't have time. But what we found, let me give you. I didn't put the slide here, but let me give you which I think is interesting. We did study these objects, okay, Herbig AB objects, okay, and then we compared this orientation here of the envelope. We compared the ambient magnetic field from stars shining through the ISM, and what we found, there was a correlation, clear correlation between this orientation here and that of the ambient magnetic field. So if you remember that classic picture of disk formation of low mass stars, right? That we have that. Thank you. That's half of the age of the universe for me because I'm about to end. Thanks, but thanks anyway. So that hourglass picture, right, of magnetic field, and then the envelope, the disk of the young star just collapsing along the magnetic field lines, you know, fits right into this picture here. So it was very nice. It was very so just polarimetry is like having a high resolution view of the star without having adaptive optics or anything. Okay, so solar system, of course, there's people in the department working with asteroids and things like that. So it could be an object for South Pole data as well. So finally, for people into polarimetry, there's going to be, I'd like to tell you, this is fairly new, it's up in the past week or so. There's going to be this, the next event of the Astropole series, Astropole Astronomical Polarimetry. This is going to be Astropole 220. So it will be in Hiroshima, Japan. So I invite everyone who are interested in polarization or just anything astrophysical, because we're going to have talks on CMB, blazars, radio data, near-infrared, optical, UV, etc. So it will be a nice environment, I'm pretty sure, as the university, and then that's where the center of conference center in Hiroshima, where the the meeting is going to take place. So summarize, we think it's an interesting, up to now, unprecedented undertaking. The optical, many things will be touched upon by the data of South Pole. It's photon noise limit, so that's very encouraging. And I'm sure, as I mentioned, sprinkled around over the slides, it's very apt to observe targets of opportunities. I think the idea that I'm just learning today of this network for targets of opportunity, let me call it that way, I think is very, very appropriate. I think it fits fairly well in that picture. Thanks for your patience.
Questions?
What sort of time resolution can you get with South Pole?
It depends on the error that you want, of course, and the magnitude. For instance, we have done very bright objects, LNA, very high accurate polarimetry. So you have to go with a minimum of 4 integrations, 4 wave plate integration. It could be 3, I guess 4 would be better, 4 wave plates. So for instance, Claudia Rodriguez's work on cataclysmic, she does observe, she keeps rotating the wave plate, and then she kind of, for instance, for the first 8 positions, she gets a point, and then she gets the second through 17th and another point, and so on and so forth. So you kind of have you kind of slide through the wave plate positions and get a few. I think she gets like a few minutes, 5-10 minutes. It really depends on how much signal to noise you want in the error. Of course, in cataclysmic binaries, you can, for instance, if you measure circular, it'll be like 10%, like a polarimeter stream, 10% polarized. So you can get by with, having higher time resolution. But yeah, it'll be it can be anything, but because the wave plates, for instance, at least in the polarimeter, they move very quickly. They move quickly. Yeah. So yeah. So but it really depends on the brightness and the error that you can tolerate. Yeah. Sorry, I hope I answered your question.
So I got a bit confused at the beginning. So at the beginning, you showed an image of a 4-channel polarimeter.
Yeah, that was just. I was just talking to people who are working polarimetry in Brazil, okay, in São Paulo.
So that was in South Pole.
That's Claudia Rodriguez 4-channel polarimeter. I'm sorry. Yeah, sorry. Yeah, sorry about that. I tried to be helpful, but okay, maybe I confused. Yeah, it's someone who works at the Space Research Institute in São Paulo. It's a little 100 kilometers from São Paulo, and she's building. Actually, she has built this 4-channel polarimeter, 4 CCDs. Simultaneously observing the same field, like a 5 arc-minute field at 1.6 telescope, 1.6 meter telescope.
So another question then. So with South Pole, how long are you expecting it will take to do the
survey?
Sky survey.
Yeah. Okay.
Southern sky survey.
Yeah. As I mentioned, we are in negotiations with, because the thing is, the idea would be. First of all, our first reaction was to get another telescope. But at CTIO and ESO, they have telescopes which are being less used over the years, and people are moving towards larger telescopes. So one of those we will try. Doesn't mean that we don't know yet. So I'm saying maybe a couple of months we'll know more. So we'll try to negotiate something like that. So we'll take a telescope and then refurbish it to make it robotic, and then put the instrument there. Yeah, that's what. So the whole survey, that's what you're asking, we're talking about, depends on the size of the telescope. For say a 2-meter telescope, okay, 2-meter telescope, we can do the survey in a couple of years, in a single color. Maybe 2 colors will be 4 or 5 years in 2 colors.
I guess it will depend on the field of view of the instrument.
Yes, right, exactly. Yes, absolutely, yes.
The field as well, right?
Yeah, the one where we commissioned, I mentioned this morning, the T80 where we commissioned, it was like 1.4 degrees per side on the side. So a smaller telescope, of course, you can get a larger field of view, typically. So I'm confident that we can get to at least one square degree. Yeah, 1 square degree would be a compromise. A larger telescope may be a little larger with a 1 square degree. But so typically we are talking about a couple of years for a single, which is not too bad, right? I mean, we have everything in place. I mean, we know the instrument works. We have the pipeline. We have hopefully, so hopefully we'll, yeah. If you, yeah, that's the idea.
Can I ask another question?
Please. Yeah.
So I think I spoke to you sometime at a conference and mentioned the fact that there's this other program which he's the PI for.
Okay. Yeah, is that what you were talking about?
Yeah. Called Wallop.
Right,
which is essentially has the same science drivers.
Okay.
So the fact that they're both going to be looking in the southern hemisphere, it would seem to me to make sense to work together to make sure that you don't sort of duplicate things and rather decide to survey different parts of the sky. So
yeah, sure. Yeah, okay, sure.
Would you be amenable for that sort of?
Sure. Sure. Yes. That'll help us complete the survey last time. Yeah. I'm sure. I'm open to discussing that. Sure. Yeah. Of course, this. I built, this instrument. We applied for money to FAPESP. I think just 30 seconds. It was built in 2010. Okay, talk about patience, right? So we got the money after 1 week, one month of 3-4 international referees. So we got the money, we built the instrument, it was ready by 2013, 14. So that was the hope was to use with T80, which unfortunately didn't turn out to be possible because of the S Plus survey. So yeah, so we didn't quite agree on that. So yeah, so yeah. Anyway, so things began to slide over. So but yeah, so you have to be patient, right? If yeah, nobody gets to be 70 impunity, I guess. Okay. All right.
Thank you very much.
Thank you.
Alex, while you put the talk on the pen drive, are you okay if we swap and Stephen gives the talk first and then you give the last so that we don't lose so much time in the process? Yeah? Okay, so. Okay, we are getting there. So that's the penultimate talk of the day. It's by Stephen Potter from South Africa, and he's going to talk about the Intelligent Observatory project. Okay.
Pointer anywhere? Pointer. Thank you. Okay, good afternoon, everyone. Let me start by introducing myself and where I'm from. I'm Stephen Potter. I'm an astronomer at the South African Astronomical Observatory in Cape Town, South Africa. And the SAO is part of the National Research Foundation of South Africa. And Eunice there is from the corporate offices of the National Research Foundation. And in turn, the National Research Foundation falls under, sorry, this is now out of date. The NRF falls under the Department of Higher Education and Science and Technology, which Takalani is here representing. So the NRF actually oversees several national research facilities of South Africa, not just astronomy, but other topics as well. And besides the SAO, it also oversees the SARAO, which is the South African Radio Astronomy Observatory, which is responsible for overseeing the operations of MeerKAT. Okay, and this year, 2019, the NRF is celebrating its 20th anniversary. So just to remind you where the SAO is, so the headquarters of the SAO is in the city of Cape Town in South Africa. But the observatory of all the telescopes are located out in the arid Karoo near a small village called Sutherland. That's about 380 kilometers. Johannesburg and Pretoria will be another 1,000 kilometers over there somewhere. The headquarters, this is the main building of the headquarters in Cape Town. The site of the headquarters will be celebrating its 200th anniversary next year in 2020. As an astronomical institute, so we'll be having lots of celebrations next year. Okay, so what I want to talk about is a new program that we've begun to upgrade the operations of the observatory to become more relevant in the modern day of multi-messenger astronomy. And we're calling this the Intelligent Observatory Project. It's also sometimes called the African Intelligent Observatory. So this is what I want to tell you all about. So to start with, I want to describe to you what the capabilities of the observatory is right now as it stands. And rather than give you a whole list of all the telescopes and things, I'm going to tell you what our involvement was in the 1708-17 GW event and how we partook in that, and describe to you the instruments and telescopes that we have that got involved in that event. And then some new current and new facilities, how we're changing the way we operate our telescopes, and finish off with some future prospects. Okay, so the gravitational wave, as you remember, this was the the gravitational wave event as a result of two merging neutron stars, which was picked up by LIGO. And what was great about this was it was also picked up as gamma ray bursts by the Fermi and Integral satellites. And so consequently, with the error regions on the sky, they were able to pin down a narrow region on the sky where you could start looking for the optical counterpart to this gravitational wave event. And the SWOPE telescope in Chile was the first to announce an optical counterpart, and you can see it there. It was detected just short of 11 hours after the event. So then about 14 hours later, I think, it came into view in South Africa. And so this image was taken with our SAO 1-meter telescope. And you can see here, here's the host galaxy, and there's the optical counterpart to the gravitational wave event. And I'm quite proud of this image because this was also the first light image for remote operations of this telescope. So as I was driving back from Solent to Cape Town, there's a hectic email flurry of there's an optical counterpart to this gravitational wave event. So I went straight back into my office and remotely connected to the telescope that I left behind the following night. And you can see just 2 nights later, the optical counterpart had disappeared through this telescope. So several of the other telescopes also followed up on this. We also host 3 1-meter telescopes from the LCO network, and that followed up in the optical. We also have a master telescope. Remember, this is a program we have with the Russians. That followed it in optical as well. But we also have an infrared telescope. That one there on the end. This is a fairly modest 1.4 meter simultaneous JHK infrared telescope. And you can see just from this plot how important even just a modest telescope with the correct instrumentation, for this event it was able to follow it, take infrared images of the infrared counterpart for 2 weeks. The optical had gone faint quite quickly over just a few days. So even with this modest sized telescope, as long as you've got the right instrumentation, you can do some nice things. And of course, I think David showed this earlier this morning. SALT there in the background also followed it up with optical spectroscopy. And you can see here these are other optical spectra from other facilities across the world as well. And this was a great result for us because we got one of the earliest optical spectroscopic follow-ups. So this image made it into the first multi-messenger paper on binary neutron star mergers, and there's SALT there right at the top. So you can imagine this event. Actually, I described this event at the India BRICS meeting, which was in 2017. And I think then it was all still secret. So even though I think every astronomer in the world knew about it, none of us were allowed to talk about it. So I kind of spoke about it but didn't name it. But now I can tell you all about it. But it was a very hectic event. If you look at the number of authors on this paper, 3,600 authors. So this was a massive organizational efforts and secrecy campaign to get this event. And there was also over 700 institutes listed on this paper. So the number of pages listing the authors and the institutes was probably longer than the scientific content of the paper. Okay, so that's a few of the facilities that we have. And so just to list a few of the other ones. So we also have more and more automated telescopes. So this is the Monet South telescope. There's another equivalent telescope in Texas, McDonald Observatory. It's a 1.2 meter telescope, and this is a fully automated telescope. We have this, so this is a collaborative telescope with Germany. This is our new SAO 1-meter telescope. It's in that dome there. And this is now undergoing commissioning, and it's already fully remotely operable from Cape Town. And of course, Patrick spoke about this earlier, the Meerlicht telescope, which is shadowed to Meerkat, and it's located in that dome over there. As Patrick already spoke about that. I can move on. And next year, we're going to receive another telescope. It's going to be a 1.8 meter infrared telescope. So this image is an image of another telescope in New Zealand. This is the infrared telescope that's come into Sutherland. It's called Prime. It's an infrared telescope, but it'll look something like that. So it's being built by the University of Osaka, also in collaboration with the Goddard Space Flight Center. So it'll be a 1.8 meter telescope, a fairly wide field of view, 1.3 by 1.3 degrees. Its main science driver is like actually microlensing, but it will have other science priorities as well. In particular, it will have a TRO override program for transients. So this is expected to be delivered in next year sometime, May, June or something, I think. And hopefully it will be on sky in 2021. Okay, so new observing modes. So traditionally the observatory has been offering observing time through the usual call for proposals, either trimesters or semesters. And the observer would go to Sutherland for a week at a time to use our telescopes, right? But now we've gone through an upgrade program. These two telescopes were kind of the main workhorse telescopes of the SAO, a 1 meter and a 1.9 meter telescope. These have been upgraded now that they are fully remotely operable from Sutherland, from Cape Town. A new 1 meter telescope was built to be fully remotely operable from the beginning. The Japanese South African infrared telescope is also remotely operable. And of course, SALT is also remotely operable as well. It can be, even though it's mostly operated in Sutherland. So to remotely operate all these telescopes, we've been building a remote control center in Cape Town. This is an image of one of the remote control stations. So this was a proof of concept to make sure that we really could remotely control the telescopes from 380 kilometers away, because you can imagine there's a lot of ingredients that makes a telescope remotely operable, one of them being a stable internet connection for a start. So this was a proof of concept, but we have more ambitious plans to convert this large room. This is a library room in that main building in Cape Town. We're going to make this a large remote control center for all our remote control telescopes in Sutherland. I listed 6 of them in the previous diagram. And it's going to look something like this. This is an architect's design of what we're going to build. So it's a bit of an overkill for astronomers and scientists, but given that next year is our 200th anniversary, we want to make this look good, because now it's going to be located in Cape Town. I mean, Sutherland is a very remote place. Not many people can go to Sutherland. Very few privileged people, to be quite honest, can go to Sutherland and see what we do astronomically in Sutherland. But this will bring Sutherland to Cape Town. And we will show directly astronomy in Cape Town to the people of Cape Town and whoever comes through. Okay, so let's talk about what do I mean by the Intelligent Observatory. So the Intelligent Observatory project, so the remote control room, the upgrades is all part of this. What effectively we're doing is we're taking the SAO into the 4th industrial revolution, okay? And if you remember, so, too many clicks, sorry. So our vision of the Intelligent Observatory is basically this. You can see all these telescopes here. There's almost about 20 of them, I think. We want all of these integrated into an overall intelligent observatory. So instead of presenting individual telescopes where you apply to them on semesters basis, for example, we want to present the whole plateau as a service to the astronomical community. So basically, we want to coordinate science across the entire telescopes of the observatory. And effectively advance, to do this, we're advancing SAO into the fourth industrial revolution. And what do I mean by that? Well, if you think, if the third industrial revolution is everything to do with the development of computers, cameras, TV screens, the internet, multimedia, what's the other one, Facebook and all that sort of thing, and automation, then the fourth industrial revolution kind of builds on that. It will be the merging. Not only will it involve new technologies coming along, but it will also include the merging of humans with technology and software and algorithms and all that sort of thing. So this is what the Intelligent Observatory is all about. And also, the aim is to enhance our national and international partnerships. Now, I didn't mention at the beginning, the reason why SAO exists, our purpose is to provide a research platform for basically you, astronomers and researchers, to do optical and infrared astronomy. So everything I'm describing here, we're trying to do to suit the astronomical community, right? So it's your feedback I'd like to have as well. So we're here to better serve the community of users, and what we want to do is to enable you to be able to submit proposals at any time. So instead of operating these telescopes in the traditional semester basis, which is not necessarily in line with the science you want to do, when you have a scientific idea, you'll want to observe it to an observatory there and then, and that's the sort of service we want to supply. And also to enable science on any time scale. So there's a science priority here to do transient and time domain science. And that doesn't necessarily fit in with semester allocations of time and that sort of thing. This will enable you to do science on any time scale, whether you want to do, say, nightly monitoring for 5 minutes of one target over a few months to you want to observe for a whole week in one block. All those sort of timescales we want to offer. And with the upgrade of the telescopes to automation and remote control, we want to be able to offer the ability to either go to Solent yourself and observe, or put it in a queue, like for example for SALT, or service observing, or remote observing. And also upgrade it. The whole idea is that the intelligence will be able to respond to alerts as well, whether it's computer-generated alerts or alerts from other facilities. So I should say as well that this project has also received funding from SARAO, the South African Radio Astronomical Observatory. So it's a joint collaborative effort. And we've identified 4 work streams, if you like. This is where all the effort in this project is going to go. So you can imagine, to get the telescopes and facilities up to the sort of requirements for this intelligence, they're all going to have to be able to, there's a lot of work to go into the control electronics and software control. There's also going to be a lot of effort into the data science software aspect. We're going to need a lot of pipeline data products, kind of automated data pipeline products. There's also a stream of work where we'll look at machine learning intelligent type algorithms in order to intelligently and automatically respond to alerts, say, from all these ground-based observatories as well as space-based observatories, current ones and near-future ones. But we're also looking at the way we operate and manage the observatory as well. So we're going to break away from these 1 week allocations, for example. So we need to look at how do we change the way that we allocate time on telescopes? How are we going to manage accommodation and transport between Cape Town and Sutherland and other support services? But also, importantly, is working with our partners in this project as well. So Russ spoke about Alifu earlier, and of course you here as well. You're our partners in this as well, our bilateral agreements. And with other networks around the world as well, that are also automated, like the Growth network. So that's my summary slide, and that's all I've got to say for now. Thanks.
Okay.
Thanks for your talk. Very, very nicely summarizing everything you've done or doing. Just a question: when you say I suspect you're going to put the robotic telescopes, the robotized telescopes, in the mix, right? Is that correct? Are you going to include the telescopes which are robotic that you mentioned?
Yeah. So there's a lot of telescopes
in
the whole intelligent observatory. Yes. So
yeah, okay.
There's a whole range of telescopes here. Many of them belong to SIO solely. A lot of them are collaborative joint projects. And they're all in different states. Many of them are all fully automated. Some of them are fully robotic. Some can be remotely operated. So it's a whole mixed bag, yeah.
Okay, thanks. Yeah, what my question then is, when you say Q observing, is that what you mean by using the robotic telescopes then, or the robotized telescopes?
Not necessarily.
Or not necessarily. Okay, that's why I wasn't
Not necessarily.
clear.
So what we'd want to offer, you can imagine, is the whole plateau as a service. So if you have a scientific idea, all you need to define is, do you want to do photometry or spectroscopy, infrared or optical? And then we will cleverly allocate it to a particular telescope. You may also want to say, well, I want to go to Sutherland myself and do the observations, and then you will be allocated, the 1.9 spectrograph, for example. But if you want to do a faint target and spectroscopy, then you would submit it to SALT, the larger telescope, and that would be a Q-scheduled observation.
Okay, so yeah, I guess what I meant is that by Q, you would. So it's not that you would have. So would you have people to do that? I mean, that's my question. If I submit for a Q observation, will you have people? If I don't go there and if I don't do remote observing, and if the telescope is not robotized, would you have personnel to do that? That's my question. To execute that.
Yeah, at the beginning we're going to have to do that. The whole intelligence automated process it's a difficult thing to do, but that's the direction we're going to move in. Yeah.
Okay, thanks.
Thank you for interesting talk. So I have two questions. So, a lot of telescope, and each telescope belongs to different organization. How you can arrange a different organization? How to force different organization for your intelligent observatory? So it's not so easy. Maybe some institution will not follow your intelligent observatory and to include data and operation in intelligent observatory. What's your opinion? Is it possible to gather all?
That's a very good question. So you're right, it's a whole mixed bag of different collaborations. But at the core, this is where we would begin. With the telescopes, we already have almost full control of it. So initially, you can imagine these three telescopes, which are fully under our control. They would be the first ones under this program. And SALT as well, that's going to be tailor-made, for example, to automatically respond to alerts from other telescopes in Sutherland, like the massive telescope. And also the LCO network, we have time on that network. At the moment,
But some part-time, not full-time.
we have a percentage of the time on it. And it's up to what we do with that percentage of the time. So at the moment, we let it available to the whole community. Every semester we put out a call. But we could quite as well easily say, we're not going to put any call there anymore. We're going to allow proposals to come in any time, and we'll submit them onto the LCO network
So the second question, when you would like, or not would like, but when you schedule to implement observation from anywhere, so on your second or third slide, or maybe fourth slide, was a aim to observe observe from Sutherland, Cape Town, or anywhere. So when you Cape Town or Sutherland are already implemented, but when you schedule to implement observation from anywhere. The question was when. When, not how, but when. It was question very simple. Thank you. I understand. No answer.
It's just a fast comment on that question. I think from Cape Town to anywhere, it's very simple. We made this experience on the Pico dos Dias Observatory in Minas Gerais State from the LNA. We set the remote control for the telescopes, and we specify in a very small bandwidth. We don't need a very stable, high bandwidth. We did the first tests, and now the telescopes you can observe from your house, from the university, anywhere. And the test we did is working fine. People observe from anywhere. And my experience on the Brazilian observatory here is that from Cape Town to anywhere is just a few months. In emergency cases, yes. Yeah, if something goes wrong, you have a lightning, and the internet goes down, our technician runs and closes everything. Yeah, you have to have somebody there.
Yeah, there are many interesting points concerning to this in practice. How much of this intelligent telescope is going to be like a smart city, or I mean, depending on the clouding? Okay, so you can say all the stuff is going to be Internet of Things, or you are planning to have not the cloud computing stuff, but a kind of foggy computing, a special one to the observatory.
all times you'll get a problem with hackers. We have a robotic telescope in our observatory, but we do not use it because it's so dangerous. If you can imagine if somebody will get a wrong command on salt.
New power, new threats. Yes. No. So I have a quick question. So, do you foresee the possibility of having some intelligent telescope allocation time and scheduling? For example, you send a proposal that needs photometry and spectrometry, and you can do that with 2 or 3 different facilities because they have similar capabilities, or and there are other proposals competing for the same time. Do you expect your kind of intelligence to also allocate the time in the facilities, or you expect someone to tell beforehand which telescope to use?
Yeah, that's a good question, and also to sort of answer in a different way. You could have a proposal in that says, I want to do photometry on something, but I don't want to define the telescope.
Yes.
I just put it in there.
Exactly.
Whenever a telescope becomes available, I don't care whether it belongs to
With these characteristics, yes, with this.
You put it in there, and the intelligence will work out. This telescope's available on this night tonight. It's got the filter set. It will go and do it.
You can even do part here, part there, and you save time. Yeah.
So there'll be an intelligence to manage all that. But then you said, but then there's the TAC process. That's a bit more tricky. I'm not quite sure how we're going to do that yet. But there's going to be humans involved in that to begin with.
Well, they are talking about substituting the judges by artificial intelligence. That's the way to go with the tech as well. Okay. Thank you. Okay, so very last one. Can you help me with the kids? Is it well connected? O meu frouxo. É horrível esse negócio. Cuidado com a cabeça. Ah, usou a lateral? Ah, perfeito. Vamos tentar em cima.
Mas o pendrive já está aí. O pendrive já está aqui. O pendrive aí põe na próxima. Funcionou bem.
Ah, it's kind of it's tighter. Okay, let's see. Where is it? Tem outro pendrive aí? Isso tem a ver com o quê? Com o controle. Não. Ok. Você quer tentar com o meu pendrive?
While we wait, just to inform that the picture of the event will be tomorrow morning on the coffee break outside here, on the close to the old wall. Okay, tomorrow morning on the coffee break we will have the official photo of the meeting.
Not really. Melhor você pôr no meu.
E coisa, Macintosh, alguma coisa?
Macintosh, pois. Tenta por. So we're going to get a less technological. E também tem gente que não sabe. So just while we wait, so tomorrow I'm going to go back to this point again in the summary, this final discussion. But I mean, as Bruno mentioned this morning, there is the possibility that the proceedings of this meeting be published by the Brazilian Academy of Sciences. I don't think there have been proceedings of previous BRICS meetings. Were there? Did you have proceedings in previous BRICS meetings? No. So we thought this could be a good opportunity to put down on paper in a kind of journal format, the things that we have been discussing, and also the proposals for doing things with the BRICS. I don't know if this will be, we wish this to be openly available for other people to read, but it could be an interesting way. Anyway, we are going to discuss this again tomorrow, but start thinking if you wish to send your contribution as a journal paper. And because if we have a good number of publications, we can have a special volume. Then we can maybe do something nice that calls attention. Yes.
This proceeding, and tomorrow say who wants, and we raise our hands and say, okay, lots of people.
That can be arranged very freely. I mean, we can discuss that tomorrow as well. So what the Academy of Science said is that they are going to make their online journal available. It's indexed, it has good, reasonable impact factor, and they let us decide the details. So I think we can tailor that to our needs. Anyway, okay, so it's the very last talk of the day. That's about the Bingo Radio Telescope project. And our co-host from the Space Institute in São José is going to give the talk, Alex.
Okay, after all this delay, I owe you guys a beer for all of you. Sorry about that. Okay, the reason I wrote a project update because I presented this last year at the BRICS conference in South Africa, and there has been a lot of advancements from that point. It was about a year ago. So I'll give you a quick overall of the science that's behind Bingo and what we have done so far. So there'll be a quick cosmological motivation, the concept, the subsystem status, and the current status of the telescope. And before you ask why Bingo, this is the acronym. We come with a funny name first and then try to fit the words inside it. Okay, the first motivation comes from cosmology, and it's due to the current times, current ages where we have a lot of cosmological data from optical surveys, from cosmic wave background surveys, now from gravitational wave observations. And we still have a few problems which are unsolved that have to be tackled. Maybe two of the most important are if inflation actually happened, and CMB will be able to give a response to that if you observe B-mode polarization, as Antonio Mario mentioned before. And what is dark energy? What's its effect in the expansion of the universe? Is it a single role mode? Is a phantom model or whatever things you can find here? And there's a number of surveys in different times in hyperspace that can be used for that.